Good afternoon, everybody, and welcome to the Fall 2021 Virtual Showcase. My name is Tim Urban. I'm the director of the Texas Space Grant Consortium, and with me online today are Talia Jurgens and Angelica Cruzinga. We're very pleased to host 17 teams for the design challenge this semester. We have teams representing 12 different schools across Texas. Today's presentations will follow our opening speaker. We'll have 8 team video presentations, 3 sessions with 2 10-minute breaks. Each team is given 15 minutes, 10 for their presentation and 5 for a Q&A. And all of our Q&As for our opening speaker, as well as our teams, are going to be hosted through the slido.com app. So visit slido.com, enter the code TSGC 2021, and you can write in your comments, upvote questions, and we'll use that to moderate all of our questions today. If you have questions during the showcase, you can email us at designchallenge@tsgc.utexas.edu. And for more information for the agenda for today, go to tsgc.utexas.edu/challenge. All right, and at that website, you can get the agenda for today, as well as links to feedback for the teams. You can view their short 1 to 1.5 minute videos, their online posters, as well as the recordings of today after the fact. Here's what today's schedule looks like. Session 1, we have our opening speaker, and then we're going to do those introductory videos, followed by 3 teams, Texas State, University of Houston, and San Jacinto College. After a short break, we'll come back with Lamar University and Texas Women's University, and then wrap up today's session 3 with UT Tyler, UNT, and UTEP. Again, if you have any questions, there's our email address in the lower left and our website on the lower right there. All right. All right, it's my pleasure to introduce our speaker for today. Montgomery Goforth has over 30 years of experience in space and defense. He joined NASA in 1990. He's worked on the International Space Station, started work on the laptops, became chief of that branch. He's worked in avionics, flight software, became chief engineer. He's worked with robotics, lunar exploration, constellation program, and now is part of the engineering directorate in strategic pursuits and partnerships, focusing on the framework for human spacecraft and technology and supporting the lunar and Mars exploration. So I will turn it over. Monty, it is all yours.
All right, well, thank you, Tim. I appreciate it. Thank you for the introduction. Let me go ahead and share my presentation. And Tim, would you confirm for me that you can see it well?
I do see it. Looks good.
Okay, very good then. Well, thank you for inviting me to this. I enjoy doing this. I've done it, I guess this is my 3rd time to present to this group, and I've always enjoyed it. I really like what the Texas Space Grant Consortium does, and I appreciate being allowed to be involved in it. Today, I'm going to talk about the Artemis program, and I'll touch on a few other things that relate to it, and generally NASA's exploration activities. I've tried to cover activities across NASA, but I probably focused a lot on JSC because that's what I know best, but I'll see if I can't touch on a few other things as well. As a first step, let me talk a little bit about how you can think about NASA overall. We're composed of 10 centers and 6 other facilities, all of which support 1 or more of 5 mission directorates. The first of these mission directorates is aeronautics research, which is just what it sounds like. It's all associated with terrestrial aeronautics. The second is science. That includes Earth observing missions, planetary science missions, and life sciences in general, human research, if you will. The next is the Space Operations Mission Directorate, which is generally focused on humans in low Earth orbit and then commercialization of low Earth orbit as well. Then there's the Exploration Systems Development Mission Directorate, which is focused on things in lunar orbit, lunar landing, and lunar surface operations, so a little bit further out in the future. And then the Space Technology Mission Directorate, which from a human perspective is generally focused on Mars transit, Mars landing, and Mars surface operations. But it also covers a lot of science type stuff, and it covers that across the board. It's not just Mars related. It's a science portfolio that encompasses all of NASA's missions. These mission directorates, they overlap each other. For instance, life sciences, even though it may be focused in the Science Mission Directorate, all of the other mission directorates have some aspect of life science that they're engaged in as well. And so they all try to help each other, and every one of these centers supports at least one of these missions directorates, and I think almost all of them support more than one. I'd be hard pressed to tell you one that didn't cover at least some aspects of more than one. So now let's talk about what's going on in low Earth orbit. First is the International Space Station. It's routinely circling the globe every 90 minutes at about 17,500 miles an hour and 250 miles of altitude. It's been permanently manned since November 2nd, 2000, so a little more than 21 years now. Most of you probably haven't even been alive that long, and certainly I don't think any of you would remember a time when there hasn't been someone on orbit. Another way to think of that is during most or all of your lifetimes, not every human being has been on the surface of the Earth. There have been at least 2 in orbit around the Earth, and as many as 9, I think, at different times. So that's a pretty interesting thing to consider, and a lot of people forget about it. It is the 3rd brightest object in the sky. The only 2 brighter are the moon and the sun. It's about the size of a football field, and it has a pressurized volume, a habitable volume, equivalent to about a 5-bedroom house with 2 bathrooms. So we use it for life science experiments, physics experiments, and Earth observation. And in the last few years, we've moved more and more towards doing applied research associated with exploration, and I'll touch on some of those things as I go forward. So that's Space Station. Well, we have to supply Space Station, and we have a commercial resupply services program. We've been flying multiple logistics resupply missions ever since, using this program ever since we retired the space shuttle. It's been 3 or 4 of these kinds of missions, plus Russian missions where they generally fly about 4 Soyuz and 4 Progresses a year. And then the other internationals, the European Space Agency and Japanese Space Agency, both fly 1 or 2 every 1 or 2 years. But our 2 contractors, the U.S. contractors, one of them is SpaceX. Everybody knows about SpaceX. They've been doing this for a long time and very successfully now. They're Cargo Dragon. One of the very cool things about Cargo Dragon is that it has a return capability. It comes back to Earth and splashes down, and we can bring science back. We can bring broken equipment back and refurbish it and fly it again. All kinds of things that gives us an advantage where to be able to bring things home is a great advantage to us. And it's the only capability like that we have other than the manned missions where, of course, they can only come back with very small amounts of payload in addition to the humans. Then we have the Northrop Grumman Cygnus spacecraft. It does not have any sort of return capability. In fact, we burn it up in orbit. Its normal mission profile, it launches from Wallops Island on the East Coast, and it will fly to Space Station. We will unload it, unload all the supplies. We will put trash back in it, and then we will release it from Space Station and deorbit it and allow it to burn up in the atmosphere. Now, it has a really interesting capability, though, that it can launch CubeSats. So usually between the time we detach it from space station and deorbit it, it launches a number of CubeSats and other small satellites to perform other missions, and that's been a very cool feature. In fact, the Cygnus that's up there right now, it's going to detach and it's going to launch a small satellite, a small capsule that we're going to allow to re-enter Earth's atmosphere separately from Cygnus, and we're going to use it to test some heat shield technology that folks have been working on. It's actually a University of Kentucky project that they got funded through, I think, Science Technology, or Space Technology Mission Director. So those are two very cool capabilities just from the standpoint of logistics resupply. And there is one other upcoming in the near term, what's now known as Sierra Space. It used to be Sierra Nevada Corporation, but they spun off Sierra Space. They are developing another resupply vehicle, another cargo vehicle that looks like a small space shuttle. It's called their Dream Chaser. It will launch on a rocket and then land on a normal airstrip. It's supposed to launch sometime in 2022, but I don't have anything very definitive on that, and I'm not sure if it'll actually make that year or not. So that's the commercial resupply. We then have commercial crew. Of course, the big player here is also SpaceX. They have flown a number of flights. I think they're up to about 5 manned flights now. Most recently, I think early last week, we splashed down a crew. And then a day or two later, we launched another replacement crew, and it has since docked with space station and is cruising along. They've done extremely well. I'm very proud of them, very happy for them, and it's allowed them to build up other things that you'll see in the course of this presentation. There's also another player out there. Boeing has what's known as their CST-100 Starliner. They actually launched this vehicle back in December of 2019. It has had some problems actually with its clock, which created some other problems, and they were unable to dock with ISS on that mission, but they were able to return successfully, and they actually conducted the first land-based touchdown in the United States of a crew-capable capsule. The Russians have been doing it for years with Soyuz. This is the first time we've ever done it as the U.S. In addition to the clock problems after that mission, they found some other issues that they've been working on. They're now having some RCS jet problems, I believe, and trying to work through them. And right now, they're planning their next unmanned spaceflight sometime in 2022. I don't think they have a month even picked out yet. And if that's successful, then they'll fly their first manned flight sometime after that. There's also a couple of new things on the horizon here. There's a company called Axiom that is actually working towards private astronaut missions in 2022. I think they're going to fly them on a Dragon, but they will have done their own private work and training of the astronauts. It might be something like a space tourism kind of thing, but they're also working towards more scientifically oriented private astronaut missions as well. And then they're also planning a private ISS module. They're going to attach a module to the ISS that they own, and will provide a few services, but that's about it. And that will come sometime in the future. I'm not sure what year, 2024, 25, something like that. So those are kind of the neat commercial crew things going on. And so now I want to move on to where we're going with the Artemis program in particular. First thing I wanted to show y'all is the Space Policy Directive number 1. This was signed in December 2017. It establishes our long-term goals for human spaceflight. I'm not going to read it, but I want to point out a couple of things. First of all, it says we're going to lead these efforts, not that we're going to do them all. It also doesn't say that NASA is doing this. It says the United States is doing this. And then it talks about a long-term sustainable capability. And that means sustainable in a way that will allow us to do other things like go on to Mars. So what we're trying to do is to build a sustainable space economy. We want to transition support of low Earth orbit to commercial entities, which we're doing with the commercial crew, and then ISS commercialization and other things, and then leverage those commercial entities to go onto the moon, we'll be in a position where NASA as an agency will take the big financial and technical risks, prove things can be done, and then transition this kind of work to commercial entities. And all of that's led to the Artemis program, which has the stated goal of landing the first woman and the first person of color on the moon. Originally, this had a 2028 target date. It got accelerated by the Trump administration to 2024. I think that was an aggressive schedule to kind of sharpen our focus. Also had some political motivations. Recently, in just the last few weeks, the Biden administration has said, okay, we're not going to make it by 2024. We're going to target 2025 right now. But more importantly to me is that they have not abandoned this mission. They are still committed to getting back to the moon. And I think that's an extremely important thing for NASA and for the U.S. space program in general. So let's talk about why are we going to the moon? There's a variety of reasons, but the big one to me is that there's evidence of water there, and that's a good thing for us. Over the last few decades, we've gotten a lot of remote sensor readings that indicate a substantial amount of water ice in permanently shadowed regions of the moon, and even some recent indications that there may be water in the sunlit regions. Now, I don't understand how that can be, but I'll trust the physicist on that. The idea of water ice in the permanently shadowed regions is that it was deposited there by comets crashing into the moon. The ice would fall into the shadowed regions, and it just never melt because it's so cold in those shadowed regions. This is all remote sensing indicated, right? We don't have ground truth yet. Ground truth is important. And if it's real, it's a big deal because water ice is exploitable. We can use the ice to make water, which is very useful to life in general. We can decompose the water into hydrogen and oxygen, which provides fuel for fuel cells and propulsion capabilities. So water plus proximity to Earth make the moon a very attractive place to go, more attractive than Mars in the near term. But it's also very important to think of the moon as a stepping stone to going onto the solar system as a whole. It's not a destination just for itself. I'd also point out that even if we're not able to exploit the water ice, the lunar regolith is known to contain a huge amount of oxygen in molecular form, and we can free that up, which will be of great benefit by itself. The water ice is almost a bonus from that perspective. Let's see. Let's go on to the Artemis program itself. I'll refer back to this chart. We call it the swoop chart. This is sort of summarizes the overall Artemis program, at least the first phase of it. It includes an uncrewed flyby, a crewed flyby. It includes precursor robotics missions, Gateway Space Station placed in lunar orbit, and then the human lander. And we'll kind of step through these over the rest of the presentation. So the first thing I want to talk about is the flyby missions. These are Artemis 1 and Artemis 2. But before I really talk about the mission profiles, let me talk about the key elements and systems. To do these missions, you have to have ground systems. You have to have a launch pad. You have to have a building to go assemble the rocket in and that kind of thing. So that's KSC has been building those up and refurbishing things they had available for Apollo for a while now, and they've done it basically. You also have to have a communication network. For the early flights, we're going to make do with the Deep Space Network, which is not a very high bandwidth network. We're going to upgrade it some for human use. We can't use the kind of communication networks that you use on Earth because all of the satellites are pointed at Earth. So we'll use the DSN, make our upgrades, and go from there. And actually, a little later, I'll talk about some of the upgrades that we need for more permanent presence on the moon. You've got to have a rocket. Our rocket is the Space Launch System. This is going to be a really big vehicle, as big as Apollo. It's somewhat like Apollo, somewhat like a space shuttle, and I'll go through it in a little bit more in detail. And then, of course, you've got to have a place to store the crew, if you will, on a mission. This is the Orion capsule, which we'll also talk about. They've both made huge amounts of progress. And let me talk through this real quick. Starting with Orion, just from a reentry standpoint, we looked at the heat shield, we looked at how the parachutes worked, we tested all of these things out. We've done water impact testing because Orion will splash down in the ocean. Once it does splash down, we've proven that's safe, and then it has to be able to upright itself as well in case it's tipped upside down. You can't let the crew stay like that for very long. We've tested the launch abort system. We've tested the service module propulsion, structural components of both the service module and the crew module. We've done the pressure vessel testing. We've done power on testing of the crew module and the service module. We've integrated the two of them together. And this picture on the right shows the two of them lumped together. It doesn't look quite like an Apollo, but it's close. You've got the same conical looking capsule and then a more or less cylindrical service module underneath it. So that's kind of the Orion testing, just pure Orion testing completed. Talking about SLS, we started out early with wind tunnel testing. We've done engine testing. We've tested the solid rocket boosters. It's using rocket SRBs similar to those used on shuttle, but they're a little bigger. They each have an additional segment on them, so they have a considerably more power. We've also done structural testing on the core stage. We've done acoustic testing of the vehicle and the engines and acoustic mitigation testing. The picture in the lower left-hand corner is water deluge testing on our mobile launch vehicle. That water deluge testing, most folks think it's to put out fires from the rockets, but it's really not. It's to dampen acoustic vibrations from the rockets, because if you don't do that, the acoustic waves have a tendency to bounce off the ground and back into the vehicle and destroy it. And that has been demonstrated more than once on flight vehicles. So that's what the water flow is all about, is damping the acoustics out. We've also recently finished what we call green run testing. I won't go through the whole checklist, but it was the big ticket integrated testing for the entire SLS core stage. And it included firing all 4 engines for the entire length of a mission, so 8 minutes, to make sure the whole system would work for as long as it had to work to get the vehicle into orbit, and it worked. So then, since it worked, we started stacking the vehicle. And these are a few images. Upper left-hand corner shows the SRB nose cones being put in place. Kind of the bottom, sort of left center, is the 2 SRBs in place, already stacked. Then the upper right center is the first part of the core stage being placed in between the 2 SRBs. And then the bottom right corner is the second part of the core stage being placed. And these next pictures are the entire stack. The first one is a view from the bottom up, from the base of the SLS up towards the top. The middle picture is the Orion crew module and service module. It looks different than the picture I showed earlier because it's in its shroud for launch. And it also has the launch abort system on top of it, so that the crew can escape if something goes wrong when the rocket is launched. And then the right-hand picture is the entire stack in the VAB with all the scaffolding around it. So you have to kind of look to see everything. But it is a truly massive vehicle, and it's going to be a really awesome spectacle when it launches. So let's talk a little bit about that, the mission it's going to go on. Now, this is the Artemis I mission. It's scheduled to launch sometime in February of next year. It won't surprise me if it slips to March or something, even a little further than that, but it's pretty close to ready to go. It has an uncrewed version of Orion, but that Orion is well instrumented for data gathering in the cockpit, because one of the main purposes of this is to make sure the vehicle will work with the crew on the second flight. It's going to launch, orbit Earth, do its translunar injection, which is, I think, number 7 on this picture. At that point, the upper stage, the ICPS, interim cryogenic propulsion stage, will separate from the Orion crew and service module. The ICPS actually continues on towards the moon and around it once, and then goes off into deep space. And on the way, it will release CubeSats. I think as many as 13 different CubeSats will be released, 5 of them in the lunar environment. And in the meantime, the Orion crew and service module will go into orbit around the moon, a permanent orbit. I believe it's a distant retrograde orbit. They'll stay in that orbit for some number of circuits, and then they have to fire a burn to come home. So that's the trans-Earth injection burn, if you will. Then it will return to Earth and do the reentry, which is the single most important thing about this entire mission, is testing that reentry capability to prove that we can bring people home safely. And that's a big deal. This is going to be a very high-speed reentry, very comparable to what Apollo did with a different heat shield, and it's a bigger vehicle. So it's going to reach Mach 32, about 24,500 miles an hour. It's going to reach about 5,000 degrees Fahrenheit. So it's going to be a pretty challenging thing to get through. And that's what we want to look for, is that success. And that, once we've proven that, we'll be ready to do Artemis II. It's a little different a mission. First of all, of course, it has a crew. Its launch date's no earlier than about May of 24. It'll take 4 astronauts into the lunar environment. Now, the big difference on this one is when it fires its translunar injection burn, it's actually going to be done by the Orion main engine, not by the ICPS, which is kind of interesting. But the main thing about it is it's going to fire that burn, and it's going to be in what's called a lunar free return trajectory. It will come back to Earth no matter what once it fires that burn. It's a big figure 8, and there's no intent to change that other than minor course corrections. Once we do this, it's going to be the first time humans have left Earth orbit since Apollo 17. So that's what, 52 years roughly. It'll be an 8-day mission, 4 days out, 4 days back. Like I said, it's coming home no matter what. We just got to make sure it comes home safely. So that's kind of the first 2. And of course, we haven't landed yet here. That's for Artemis III. But in the meantime, we will be landing unmanned vehicles through the commercial lunar payload services. This is a service contract. We are paying companies to provide a landing on the moon and data and services once they get there. We're not asking them to provide the lander itself. That's theirs. We want them to get things landed. We want various scientific payloads landed on the moon. Very quickly, looking at the key elements and systems, really it's just the landers themselves, and there are a variety of them that I'll talk to in a minute. And then also a key for us is an unmanned rover that we're going to use to search for water ice. It's called the Viper, Volatile Investigating Polar Exploration Rover. The missions, this is a picture of the moon with various past missions shown on it, the USSR unmanned vehicles, US unmanned vehicles, the Surveyor, the Apollo missions, and some Chinese missions as well. And then the CLIPS missions are shown kind of in the blue arrows and circles. The first of these, actually, this is probably reverse order. The first of these is probably Intuitive Machines landing 6 payloads at Oceanus Procellarum. And then the second will be the Astrobotic missions with 11 payloads to Lacus Mortis. It's a little unclear which one's going to be there first. They're within a couple months of each other. Then later in the year, in 2022, Intuitive Machines will land another lander at the South Pole. This one will include a drill. They're going to try to position it in a place where they can drill and look for water ice. It'll be a little hit or miss, but it'll be great news if they're able to find it. After that, shortly after that, Astrobotic will fly the Viper to the South Pole, and it will go around looking for water. Also Firefly, which by the way is located in Cedar Park. I should point out Intuitive Machines is located near the Johnson Space Center. So that's a Texas company. Firefly is also a Texas company in Cedar Park. They're going to fly 10 scientific payloads to Mare Crisium. Maston Space Systems is they're going to fly 8 payloads to the South Pole. So that's 22 and 23. There'll be a number of CLIPS missions during 24 yet, but they haven't picked them. All of those will be precursors now to Artemis III in 2025. So that, I think, is all I had about CLIPS. Very quickly, we'll talk Gateway. This is the space station we're going to put in lunar orbit. Let's see. Let's go to the next one. These are the key elements: the power and propulsion element, and the habitation and logistics outpost, the HALO. HALO is the actual man part of it. It's the pressurized version of it where the crew will stay. The PPE is the motive force, if you will. Both of these will be integrated together and launched on a commercial vehicle no earlier than November of 24. It will actually take them 9 months to get to lunar orbit because the PPE has an ion thruster, which is extremely efficient but not very powerful. So it's extremely good for us once we get into orbit. It just takes a really long time to get to that orbit. But that was the trade we made, and it'll be a good one over the long term. It'll just take a while. The next component that's important early on is the deep space logistics module. I actually think that SpaceX is going to supply these as well. It's very similar to logistics on space station. They'll bring things up in this module, unload the module, put trash in it, and then dispose of it somehow. I don't know if these will be reflown or not. That's not something I think has been decided quite yet, and it's somewhat impacted by the HLS that you'll see in a few minutes. And then there's the intent to build up Gateway over time, which I'll touch on in a minute, but I've shown a couple of the longer term configurations. One of them includes I guess the one in the upper right includes the European Space Agency's Esprit module, which just looks like a small module between the original vehicle and the Orion now. And then another one actually has an inflatable module that would give the crew a lot more room to play around in, if you will, and to live in. That's maybe a better configuration for trying out things for a Mars transit vehicle, because we'll want something big and roomy for that. Let me talk about the orbit it's going to be in. That's the orbit it is in will be in is called the near rectilinear halo orbit. It's a really cool thing. It's very useful. It looks kind of polar, but it isn't exactly. When you're looking at it from Earth, the picture on the right shows you what it looks like. You can always see Gateway when it's in this orbit. Therefore, Gateway can always see Earth, which makes it a very good communications relay location. It's also highly eccentric and spends almost all its time over the southern hemisphere. I think it's a 6.5 day period. Only 3 hours of that 6.5 days are spent over the northern hemisphere of the moon. So you get a lot of good communication on the moon as a whole, but particularly in the South Pole. You can access anywhere on the surface from this orbit. It makes a decent jumping off point to Mars. It's not the best orbit to go to Mars from, but it's a good one. It's a good orbit to go to Earth from. To go to from Earth. It's a fairly low energy access, which makes commercial resupply more viable. So it just becomes a really great orbit for general purposes. It's not necessarily optimized for any one thing, but it's good for a lot of things. It's also an orbit we've never been in before, and it's got some interesting challenges. So next year in March, we're launching what's known as the Capstone CubeSat using a Rocket Lab Electron rocket from their launch site in New Zealand. And we're going to put it in RHO. Just kind of interestingly, this will be only the third CubeSat to leave Earth orbit and the first spacecraft of any kind to go into NRHO. And we're going to use it to test out the navigation techniques we need to stay in NRHO. How much fuel will it really take to maintain the orbit? That kind of thing. So that's going to be a real cool thing to look for next year. Now let's talk about Artemis III. This is the payoff mission, landing the first humans since 1972. So at that point, it'll be 53 years. First woman, first person of color. The planned launch date is sometime in 2025. It's intended to have a crew of 4, at least 2 of whom are supposed to land. It will not make use of Gateway. It'll be a mission directly, well, maybe not directly to the moon, but it will not go through Gateway for the Artemis III. A couple of key components. One is the EVA system. You have to have a new suit. The old suit is 25 years old and it's gotten very hard to maintain. It's also only suited really for 0G. We need a lower torso for surface ops. You can't get boots on the moon without boots, and you need boots that can stand the temperature, both hot and cold, of the moon itself. We're working this replacement suit through a commercial-led project similar to the other service projects or service programs we've been talking about, CRS and HLS. It's going to be heavily involving JSC personnel because they've got the experience. We expect to award this contract sometime in the spring of next year. Then you've got the human landing system itself. Basically, Orion's supposed to get the crew from Earth to lunar orbit and back again. HLS is supposed to get the crew from lunar orbit to the surface and back to lunar orbit again. We've been working on this via commercial partnerships. We actually did the first phase of this with 3 contractors, blended government teams, each of which had a very different approach. And then we made an award to SpaceX. I think most of y'all are aware of this, using what they're referring to as their SpaceX Starship HLS. They are going to have a line of starships, I believe, for different purposes, but this is the Starship HLS. We awarded this a few months back. There are some legal challenges, and they've only recently cleared, and we've been able to start discussions with them. So since it's been so recently, there's still a lot of unknowns about the Artemis III missions. I was hesitant to include any sort of mission profiles similar to what I had for Artemis 1 and 2 because I'm sure it's not accurate. For instance, it includes a rendezvous at Gateway that won't happen. And also, frankly, Starship is a radically different design than what we expected, so we're kind of adjusting our thinking in terms of the mission concept. A couple of things I think I can say about it. First of all, there will almost certainly be an unmanned lunar landing before Artemis III. The Starship will touch down unmanned and they'll test it out and all that. When Artemis III comes along, it will launch unmanned and be refueled and checked out in low Earth orbit. Once we know everything's good, we'll launch a crew on Orion. Orion and the Starship will rendezvous somewhere. Might be in low Earth orbit, more likely to be in a lunar orbit. I'm not sure which one. They'll transfer the crew, either 2 or 4 of them, from Orion to Starship. They'll take Starship down to the surface, do their thing down there, then ride Starship back up to Orion and return to it and use it to return to Earth. The Starship itself, the first one, I'm not sure what they'll do with it. They may bring it back to low Earth orbit and refuel it. They could even bring it back to Earth itself. That's kind of up to SpaceX at this point, and we're not sure enough of what their plans are yet. I want y'all to note, too, that this contract award is to SpaceX for just the first lunar landing. We have other contracts and procurements that are being worked right now to figure out how we want to do this over the long term in a sustainable way. Of course, SpaceX probably has the most likely chance of winning those awards, but we are keeping them separate just to make sure we don't put all our eggs in one basket too soon. So let's talk about what sustainable means. When we go, we're going to probably land at the South Pole, like I was talking about, near Shackleton Crater. It gives us, that region gives us the things we think we need for a sustainable lunar base. Access to sunlight, minimal temperature variations, close proximity to shadowed regions and hence water ice, a fairly continuous line of sight with Earth, so we don't have to depend on Gateway for all communication, but mostly we do. When we get there with Artemis III, we'll start small, probably 4 or 5 will be pretty short duration, focused on learning and getting better at living on the moon. Do lots of science, sample collection, do some evaluation of what we call in situ resource utilization, basically, making use of the lunar regolith and water ice. We've also got to learn a lot about dust mitigation. Lunar dust is a nasty thing. Apollo 17 had 3 EVAs, which was the most of any Apollo, and the crew was convinced that they couldn't do a 4th because the dust had fouled up their suits so badly. So we've got to figure out a way to do lots of EVAs with a given suit without letting it get fouled up. Then after Artemis III, we'll start expanding Gateway, expanding the lunar base, et cetera, and go for much longer missions and start to use those use those to learn how to go on to Mars. And as we do this, we'll get greater engagement from our commercial partners and also our international partners. They will be supplying various components of this, of the base camp and other exploration capabilities. So this is a little bit of what the base camp might look like. I won't talk through it on this picture, but very quickly, the kinds of components I mentioned already, we've got to upgrade the communication systems in order to give them enough bandwidth for humans to use. What the deep space network is today is somewhat equivalent to a dial-up modem. We need something much more equivalent to high-speed internet. We also need a network on board the lunar, on the lunar surface. We kind of started calling this LunaNet. I'm not sure if that'll stick, but the best way to think of it is something akin to a 4G or 5G cell phone capability. We'll have to have some sort of permanent habitat. The one shown here is just a tin can. It might be something that looks a bit different than this, might be an inflatable, we don't know. It needs to have some level of radiation protection as well. We'll have to have power systems and other utilities, if you will. This is a solar power system, but we might wind up with nuclear. Just as important as how we generate power is how we transmit it. Running cables from a set of solar panels or a nuclear generator all the way to a habitat. It takes a lot of mass to bring cables up there, and we don't want to spend that much mass, so we're going to have to find better ways to do it. We've got other technologies we've got to develop as well, high-performance spaceflight computing for a lot of reasons, but one thing of particular interest is that it enables precision landing. We need to be able to put landers close to the permanent base and let them take off again. Without having to worry that we might actually hit the base, right? So we've got to have something very reliable there. We've got to have lunar dust mitigation stuff in place, ISRU. If we're going to refuel the landers from, say, the H2 and O2 from water ice, we'll need some cryofluid management capabilities and various other things on the surface. One very significant thing is that we need to have mobility. We're envisioning this right now as kind of 2 big pieces. One is the habitable mobility platform. Think of this as the RV, the recreational vehicle, and then the lunar terrain vehicle, which is more like the dune buggy. And I've kind of shown a prototype we have here at JSC that's meant for 1G, just to give you an idea as to what it might look like. Mobility is extremely important because we're talking about a really big area. The crater in the middle here is Shackleton Crater. I've overlaid on top of this an outline of Washington, D.C. in orange, and then the beltway around Washington, D.C. in red, just to give you a feel for how big it is. You're not going to be able to do this on foot. You have to have the ability to transit on a vehicle. You have to have the ability to stay in that vehicle because you can't just always keep coming back to a permanent or to a single fixed point. And of course, you'll have to bring power along with you and all kinds of things. So we're very much working towards that kind of architecture to enable exploration and ultimately to go beyond Shackleton Crater too. Let's see, I think that's kind of it on the long-term Artemis or the lunar stuff. I want to point out that all of this kind of applies to Mars. This is a list of the top 5 risks or hazards of human spaceflight. Number 1 is radiation environment. Once you get outside of Earth's Van Allen belts, the radiation environment is very nasty, and we have to have a way to deal with that for both humans and for electronics. For humans, they face isolation and confinement issues, which can create some behavioral problems. It's hard to deal with that kind of thing. Distance of Earth from Earth is a problem too, both from a mental perspective, but also from a comm delay perspective. You can't talk to anybody easily once you get past the moon a ways. The moon's only about a second and a half round trip. No, 3 seconds round trip, sorry, second and a half one way. But once you get to Mars, you're talking 15, 20 minutes one way kind of delays. So you've got to have ways to deal with that. Gravity is an issue, or we actually at this point know more about how humans perform in 0G than we know how they perform in 1/3 or 1/6 G. So we've got to figure out how to deal with those different G fields. And then changes in gravity are a big deal. It takes a while to get acclimated when you go from 1G to 0G to 1/6 G. Or more importantly, going to Mars and being at 0G for 9 months and then going to 1/3 G. You have to deal with physical weakness, you have balance issues, your reflexes are different, all kinds of things are at issue, and we've got to work on how to deal with that. The hostile closed environments, we found from space station that the stuff in space, microbes change up there. They mutate, they behave differently, and the human immune system changes as well, and is not as effective as it is on Earth for some reason. And so we've got to figure out how to deal with those and how to compensate for that. So we're going to have a lot to learn on the moon as far as going to Mars. We don't want to wait till we go to the moon, so we've started doing analog missions, which simulate certain aspects of spaceflight. It's particularly good at simulating the isolation and confinement. This is just a list of all kinds of analogs we have. Just to touch on a couple of them, Antarctic stations have been around for a long time. We can learn a lot from the kinds of situations those guys are in. NEMO is one we have 16-day missions that are conducted off the coast of Florida, underwater missions. So it's a very challenging physical environment and inherently dangerous, so that folks have to really focus. A couple I want to talk about that are at JSC are CHAPEA and HERA. So HERA is our human exploration research analog. We've been doing this for quite a while. We're on campaign number 6. We just yesterday completed mission number 22 of HERA. It was a 45-day mission with 4 crew, lots of focus on behavioral health, group dynamics, that kind of thing. Human factors, medical capabilities, and then they actually do delayed communications. They'll run 3 more missions of identical profiles with different crews over the rest of this year. And that's the way they do it, is every year they come up with a certain mission profile and then they repeat it to gather statistical information. Then we're also doing the crew health and performance exploration analog. This is a little bit more Mars-oriented. You can see it while it's under construction here at JSC. It's actually a 3D printed habitat. And we're setting up to make 1-year-long missions where folks are isolated inside this habitat. They'll have the capability to do simulated EVAs. They'll put on virtual reality goggles and be able to go out in a sand pit and walk around a little bit, but they won't be allowed to, quote, return to Earth, unquote. They'll still be under communication delays. They'll still be isolated from anybody other than the crew. But these are going to be 1-year missions. So they'll be very long missions, very stressful, I think, for the crew's mental state. And one of the things we're trying to understand is the impacts of that long mission on food and diet, because people have found that if folks eat the same stuff over and over again, they pretty much don't eat as much, and they will lose weight and grow much less healthy, and we're trying to figure out ways to counteract that. And so that's kind of what CHAPEA is about. And I'm kind of buzzing through these because I know I'm getting short on time, so I've just got a couple more slides. This one is just very quickly the things to look for next year during 2022. The Artemis I should launch in February, maybe March, but still scheduled for February. You can expect to see SpaceX Starship orbital test flights. They've been doing test flights for a while, but they're going to try to get into orbit next year.
probably relatively early in the year, and my guess is they'll have more than one during 2022. I mentioned the Capstone CubeSat to NRHO in March. There will be those 3 CLIPS landers, Astrobiotic, and then 2 intuitive machines. In addition, there's going to be lots of interesting stuff happening on ISS. There'll be a number of crew rotation missions and resupply missions. There'll be the private astronaut missions, maybe even Dream Chaser. There'll be EVAs. All of that stuff will be happening in low Earth orbit, and I can't even begin to list all of it. And then, so that's kind of the short term. Longer term, or of great interest here, is the Artemis Accords. So we're going to lead these Artemis missions. International partnerships are a big deal, a key role in achieving a sustainable and robust presence on the moon. We can't do it all by ourselves as the US. So, and we particularly can't do that and then go on with a human mission to Mars. So we're trying to negotiate a common set of principles to govern the civilian exploration and use of outer space. That's what the Artemis Accords are all about. As of October of this year, 13 companies had signed off on these. They're listed here. My understanding is a week or two ago, France indicated they were interested in signing them also, although I don't think they've signed them yet. But this is a big deal for us to kind of expand on the Outer Space Treaty of 1967 and also allow us to commercialize things like cislunar space in a way that nobody had really considered for a long time. There hadn't been a whole lot of updates to space law in the last few decades. So this is a big deal from a big picture perspective. So I've covered a lot, but I want to point out I have not covered everything there is to talk about with Artemis, and I certainly haven't covered everything about NASA. For example, the James Webb Space Telescope is going to launch in about a month on December 18th. And that's a really big deal. That's going to be an incredibly cool telescope. And I haven't even mentioned it up to now, right? I could have probably spent an hour talking about it. So what I hope you'll take away from my presentation today is we've been flying space station for 21 years, and we've been learning from it for 21 years. We're back to launching U.S. astronauts to low Earth orbit on U.S. vehicles. We are still executing our plan for going back to the moon. That plan has changed, and it will change. And NASA's role has changed, and it will change. We're making much greater use of various non-traditional approaches and commercial space partners. We'll make more use of international partners than we even did on space station. But whatever happens, NASA's going to keep developing the technology we need for space exploration, and we're going to keep moving forward in all of this. And I think that kind of concludes my presentation. And I hope we still have some time for questions, and I'm going to stop sharing and start my video. All right.
Excellent. Thank you very much, Monty. That was a great presentation on Artemis. I'm always excited to see what is on the horizon and what's coming up next. So for those online, if you have questions, please go to our Slido app, slido.com, enter the code TSGC 2021, and you can ask questions. So we do have one question here. How big can Gateway get compared to ISS?
Theoretically, it could get as big as ISS. There's no real limit, but there's no intent to make it that big either. It'll, if you think of the whole ISS as the size of a football field, I don't think Gateway will ever get more than about a fifth that big. But there is some potential that we might adapt it to be a deep space transport, and it could grow from that perspective. It's really just a matter of how much mass do we want to put into lunar orbit and for what purpose.
Okay, and then you did mention that it could be a stepping off point for going to Mars. So what would that look like?
Well, let me assume for a second that Gateway stays a space station in orbit around the moon. What we would then do is we would build a deep space transport attached to Gateway
And then at some point, once it was built up and tested and checked out and all that, we would fly a crew to Gateway and then transfer that crew from Orion probably onto this deep space transport, and then start it, do a trans-Mars injection burn, if you will, from Gateway and head to Mars. And if we're still dealing with the same kind of propulsion limitations we have been in the past, it'll take about 9 months to get to Mars. It'll kind of be up to us how long we want to stay, but it'll probably be about a year, and then we'll be able to turn around and come back on a low energy route as well. So 2-3 year kind of mission duration.
Okay, great. I don't see any more questions online. So the first missions to the moon, what are going to be the length of those, and what's the frequency?
So I think the length of the first mission is going to be relatively short. It probably won't be as short as Apollo 11. Apollo 11 was only on the moon, I think, for, less than 24 hours. I think maybe less than 16. But I don't think Artemis III will be on the moon much longer than a few days. They'll do 2 or 3 EVAs, prove that all the systems work and all that kind of stuff, and do a little bit of science and preparation, and then come home. Artemis 4 would probably be a little longer, and Artemis 5 a little longer still. And it will just depend on what the mission objectives are at that point. And really what kind of capacity Starship gives us, or whatever other vehicle we're using for those flights give us.
Okay, great. Next question here. So it's about space debris. The destroyed Russian satellite is in the news.
Yep.
How is space debris going to be a consideration, or how is that going to alter the plans?
Well, first of all, space debris is really only a problem in low Earth orbit for us, right? It has the potential to become a problem in as high as, say, geosynchronous orbit, just because there are so many satellites up there. But right now, our big problem is low Earth orbit, because that's where Space Station is. And it has the potential to be a very big problem. If people keep blowing up satellites, you have the potential to contaminate those orbits to the point where you can't put other vehicles in them. And then you have to get kind of lucky to get through those layers of debris into a clear area, a clear space. Right now, that's not an issue for the moon. We've never put enough around the moon for it to be a problem. In Earth orbit, there are people working on mitigation strategies, ways to clean up the debris. You can also count on some degree of natural cleanup, because the debris itself is impacted by the atmosphere. In the same way Space Station is as a whole, there's still atmosphere at that altitude. It's very faint, but it's enough to cause drag, to slow you down and drag you into the Earth. So we have to reboost the station all the time. Of course, the debris doesn't get reboosted. It's much smaller, though, so the drag is not as much, but it'll slowly degrade over time and re-enter the Earth's atmosphere and clean itself up that way. But I don't want to deny it. It's a problem. The issue they're having right now is a significant issue. And if that kind of thing continues, it could get to be really bad. So we need to stop it.
All right, so it's been 50 years since we last went to the moon. What do you think lunar orbit is going to be like in 50 years' time?
I think that there is a very good chance that we will have multiple companies providing missions to the moon for various purposes, including tourism. I suspect they're going to find some ways to commercially develop the moon in general, make use of resources that are there in the 1,6G environment. for manufacturing purposes and other purposes. I think it's possible that they will exploit the moon from the standpoint of providing, how to put it, providing mass to be used in further exploration of the solar system. Because it is only a 1/6G gravity well. It's not like ours, and there's no atmospheric drag to worry about. So you can launch things from the moon much more easily, but you have to get a capability to launch things, right? So that'll have to get built up. There's stories about helium-3 on the moon, tritium, I guess is how you say it, which could be a source of power. I think that's the stuff they want to use in fusion reactors. If that becomes commercially viable, it could be that there will be a growing industry there. I think there's some real potential for various kinds of commercial development. I also think there's some potential, if it can be made inexpensive enough to get there, for tourism. It's still going to be kind of millionaire kind of tourism, right? Maybe billionaire. But I could see where people would think it would be pretty cool to camp out on the moon for a month. So.
All right, great. Well, thank you very much for joining us. We've appreciated everything you've shown us, and hopefully you'll come back in some other time and share even more what the next steps are.
I'd be happy to. I've enjoyed it, and thank you very much for having me.
All right, thank you, Monty. All right, for those of you who didn't see the beginning, this is our schedule today. We're going to show the team introductory videos first. Each team has a 1 to 1.5 minute video introduction of their project, and then we'll go right into the 15-minute team presentations. So the teams are going to be on video here. We've done our best to level the audio, but you may want to have your hand on your volume control.
Has this ever happened to you? Hi, I'm Nicholas Akash.
I'm Olivia Salazar-Mendez.
I'm Jesse Smith. I'm Nicholas Gerard.
I'm Mason Huebner.
We're Team Sodas, and we got a product for you. With our proof of concept dual-use wideband microphone array system, your voice communications will be relayed and your ultrasonic anomalies will be detected. You'll be alerted with auditory and visual alerts for any and all ultrasonic anomalies.
Ultrasonic anomalies include but are not limited to leaks and failing equipment.
The system detects these voice communications and anomalies with MEMS,
Microelectrical mechanical system.
microphones. If a voice
Frequencies 200 Hz to 6 kHz.
is detected, then that voice gets relayed. If an anomaly is detected,
Frequencies greater than 20 kHz.
then audio and visual alerts will go off, indicating the intensity of that anomaly.
And now for a quick demo. This is our anomaly generator. It produces an ultrasonic sound inaudible to humans. Watch the graph as Jesse enables the generator. A spike appears at 25 kHz, demonstrating anomaly detection.
This product is important because it can serve as early automated leak detection for pressurized vessels such as spacecrafts, airplanes, and industrial equipment. Email now for more information.
We are NASA Space Grant.
Hello, my name is Ismail Ali.
Yusuf Sirajuddin.
Sami Shahid.
Omar Al-Koja.
We are Team 10, responsible for designing the antenna mounting structure. Our team is tasked with designing a prototype for the antenna mount that is suitable for space operation. Our team chose to attach the antenna mount to the Nova C lander.
Our proposed concept meets all the requirements needed for it to operate at a minimum of 20 years, although our team will need to perform physical testing to validate the device once the device is built.
Our device will be coated with a specific type of aluminum alloy to maximize durability as well as reduce radiation from affecting the device.
Our structural finite element model was validated successfully with field strain measurements using field temperature measurements and material as input. And we are NASA.
Space Grant.
Hello, I am Daniel Guerra, and I am from Team Hyperion.
Hello, I'm Luisana Padron, and I'm from Team Hyperion.
Hello everyone, my name's Jeff Gleesman, and I'm from Team Hyperion.
Hi, I'm Jordan Cyber, and I'm a part of Team Hyperion.
Hello, my name is Luis Rosario, and I'm from Team Hyperion.
The next giant leap for mankind is here, expanding our horizons out to the moon and beyond. As we begin this bold venture under NASA's Artemis program, future explorers at the planned Artemis base camp on the south pole of the moon must have access to many different sources of energy to meet a variety of needs, including life support, food production, manufacturing, and processing of raw materials. Team Hyperion is spearheading the effort to design, simulate, and develop the methods needed to produce a lunar solar concentrator that will give explorers near continuous access to energy on the lunar south pole. This undertaking requires the team to synchronize functions between a variety of tools, including CAD software such as Autodesk Inventor, Optica EM for ray trace simulations, and SimScale, along with MATLAB for thermal analysis. Success here on Earth will power our journey into the unknown.
We are NASA Space Grant.
As humanity progresses, the desire to search and explore deeper into space is ever expanding. The physical difficulty of sending humans deeper into space has led us to utilizing more and more complex electronics. With the cost of sending materials into space being high, an ever-increasing need for interchangeability is a must.
Team Vulcan's solution to this problem is a system that will be explained with the help of this block diagram. This block diagram proceeds as follows. We have a user interface, which is comprised of 3 sections. A GUI, a network to handle all data coming in and out of the system, and a storage device that can give the interchangeable controllers their behaviors. Moving on to the next section, we will have a simple Ethernet switch which will go connect to our 4 ICs.
Then, through a series of common connectors, we will connect to our data collection. These could be anything: a habitat controller, various thrusters, alarms, you name it. This is a brief overview of what Team Vulcan has been working on these past few months.
We are NASA Space Grant.
Oh, hey NASA, didn't see you there. My name's Natalie from TWU's Team Montgomery, and I have a quick question to ask you. Have you ever experienced tiredness or exhaustion related to changes in your sleep cycle? For example, jet lag?
Well, astronauts deal with a similar problem in space. In microgravity, astronauts witness the sun rise and set about 16 times per day. As a result, a disruption in their circadian rhythm occurs, causing lower levels of alertness and an inability to sufficiently complete tasks.
Several strategies are currently being used to help mitigate this issue, such as medications, caffeine use, sleeping bags, and the solid-state lighting assembly. However, these present their own problems and are not solution-oriented to best fit each individual astronaut.
That's why we have created an individualized light therapy device that promotes alertness and fights against circadian rhythm desynchronization. It's a pair of glasses that emit blue light via strategically placed LEDs. The solution is better than other current strategies because it is non-invasive, cost-effective, and portable.
This device was tested extensively by experts using high-tech measures such as EEG and PBT and all passive flying colors. So why not help the astronauts going up to space by giving them the ultimate solution to promote alertness and protect themselves?
That's what we thought. We are NASA Space Grant!
Hello, we are Team Callisto from the University of Texas at Tyler, introducing our compliant lunar sample marker for the identification process of lunar specimens.
Intended for use during the upcoming Artemis mission, the main considerations of the marker was to be safe, easily operable, and can be easily deployed and reused with minimal effort by simply flipping it over 180 degrees.
The design features a compliant mechanism with flexible joints, which allows the legs to take shape on a variety of different surfaces.
The device will also have an anti-static coating, and the interior of the body will be sealed off with a tight, form-fitting for maximum lunar dust resistance.
The self-adjustable form of the device will advance space exploration by allowing the lunar specimen identification process to be greatly simplified and usable in multiple different terrains.
Team Callisto intends to provide an improved solution for any mission, whether it be on the moon or any future destination.
We are NASA Space Grant.
Hello, my name is Ali Hamoud and I'm the team leader for Team Untitled. We are working on the Advanced Spacecraft Lighting Control System. In space, crew members will not be able to maintain their circadian rhythms, so we are creating a method to help them maintain that.
Hi, my name is Alejandro Bacallo and I'm the reporter as well as the hardware lead for this project.
My name is Nicholas Tyndall. I am the software lead for this project. In order to help with the circadian rhythm problem, we are going to be using an artificial lighting system to help align circadian rhythms both in humans and plants with that which we expect. We also hope to add a voice control system as a secondary goal. Our plan is to use a network of Raspberry Pis to control a DMX lighting system, as well as read from sensors to see the actual values being outputted by those systems. Those values will be used with a GUI interface running on a Raspberry Pi as well to control and implement our system.
We are NASA Space Grant.
Human exploration has thrived throughout history. NASA is currently the forerunner when it comes to space exploration. Research has led to believe that there is ice water present in the south pole of the moon. The problem at hand is radiation coming from cosmic and solar rays. Our plan is to find a way to design a material that would act as a black body.
Our team used the application of surface roughness and geometry to achieve a more black object. To model an ideal black body using the properties of absorption and emission.
For our design process, we created different designs focused on light scattering along the surface. For our final design, we feature a hexagonal shape with small holes surrounding the concave surface.
We metal casted our 3D printed design by pouring molten aluminum into a sand mold.
Through testing, we were able to come up with designs that could mimic a black body. We also learned that physical attributes such as surface roughness helps with the dispersion of radiation, which helps the instruments not to be affected by light interference.
We are NASA Space Grant.
All right, excellent videos, everyone. Great job. As you can see, we have 8 very diverse projects for our first 8 teams here. So students, as Talia and Angelica promote you, you're going to go from a regular attendee to panelist. Then you can go ahead and turn your video on, turn your audio on, and you'll be able to share the screen. All panelists can share their screen, so whoever is presenting the slides, you'll be able to do that. I wanted to remind everyone in the audience for the Q&A, we're going to use the slido.com app. So whether you're on the Zoom webinar or on YouTube, please go to slido.com to submit your questions for the team. The code is TSGC 2021. That's Texas Space Grant Consortium 2021. I see, looks like the whole team is here. Thumbs up if the whole team is here. Ah, the whole team is here. All right, excellent. So our first team to present on day 1 of the Texas Space Grant Design Challenge is Texas State University, Team SONUS. Take it away, team.
Hello, everyone. I'm Nicholas Eltikosh, the PM for Team SONUS. Our project is a proof of concept dual-use wideband microphone array system that detects ultrasonic anomalies and relays voice communications. There are systems out there that can detect ultrasonic anomalies, such as leaks in failing equipment. There are systems out there that can relay voice communications, such as PA systems. There are no systems, to my knowledge, which combine these 2 functions to help reduce size, weight, and power consumption. So this is the original problem statement and goal statement given to us by TSGC. As you can see, one of our goals is to be able to detect voice, which are frequencies 200 hertz to 6 kilohertz, and relay that voice, as well as detect ultrasonic anomalies, which are frequencies 20 kilohertz and greater. If an ultrasonic anomaly is detected, we are to provide the user with alerts via a graphical user interface, as well as audio alerts at a 1 hertz rate, which sonify the ultrasonic anomaly.
Hello, I'm Nicholas Gerard, and this is the overall system diagram. On the left, you'll see inputs, and on the right, you'll see outputs. Starting at the top, we have the user interface inputs. That'll be voice mute, voice volume, and alarm mute. Moving on to the MEMS microphone array, we have voice, ultrasonic frequencies, and other environmental sources. Finally, we have power supplied to the whole system. For the graphical user interface and the speaker, we have system status, visual alerts, voice audio, audio alerts, and anomaly sonification. Sonification remaps ultrasonic frequencies into the human audible range. This alerts users of the intensity of the detected anomaly. This is very similar to a Geiger counter.
Hi, my name is Olivia Salazar-Mendez, and this is our high-level block diagram for the system. And essentially, this breaks the system as a whole down into our 6 subsystems. Our subsystems are color-coded to indicate which individual will be working on which subsystem. So for green, we have Nick E, who's working on the analog filtering and amplification. For brown, we have Nick G, who's working on the output audio. For blue, we have Mason, who is working on our digital signal processing. For orange, we have myself, who's working on the MEMS microphone array and the power subsystem. And for the light blue, we have Jesse, who is working on our user interface. We also have some different colored arrows to indicate the power flow, that's going to be orange, and the signal flow in black. We are going to have 6 microphones in our array that will arrange orthogonally into the shape of a cube. We are hoping that this will assist us with the requirement of omnidirectional detection and also with the stretch goal that we have of anomaly localization. This is our MEMS block diagram. And as you can see, the MEMS microphones will be receiving an input of sound, either ultrasonic or voice. It will be converting that into an analog signal and sending that analog signal to the amplification and filtering subsystem.
I'm in charge of the analog amplification and filtering subsystem. This subsystem takes 5 volts DC from the power subsystem and feeds that through a linear regulator, which outputs 3.3 volts to each of the MEMS microphones, as well as to each stage in the analog chain. The subsystem takes in the signal from the MEMS microphone and passes them through a high-pass filter, an amplifier, and a low-pass filter, which help attenuate noise and condition the signal for processing by the DSP subsystem.
I'm Mason Huebner, and I manage the digital signal processing subsystem. Inputs include function calls from user interface for output audio controls and the analog signals from the analog conditioning subsystem. The ADC digitizes these signals, allowing some DSP functions to be performed. These include digital filters and downsampling to isolate voice audio data from one or more channels, and fast Fourier transform to calculate the spectrum data for all channels. This spectrum data is used for noise floor sampling, anomaly detection, localization, and sonification. Detection is based off the current signal magnitudes and the sampled noise floor. Localization compares magnitudes between microphones to determine a likely point of origin. Alarm synthesis is simply an alert tone, and anomaly sonification allows user to hear the anomaly. The output audio is mixed and sent to the output audio subsystem, while the detection localization data is made available to the user interface. This is an example of proof of concept showing data from 2 microphones spaced 180 degrees apart. The trigger threshold is determined by sampling the noise floor at startup and applying an offset, while the localization is determined by comparing the magnitudes between the 2 microphones.
Hi, I'm Jesse, and I'm in charge of the user interface subsystem. The purpose of the user interface subsystem is to provide a point of contact for the user to control and receive feedback from the system and to visually alert the user of anomalies. Up here, we have our user interface design concept. And additionally, our stretch goal of localization will include adding a directional vector to this graphical user interface. Moving on to our hardware block diagram for the user interface. Inputs include alarm silence, voice mute, and voice volume. And outputs include the LED indicators for anomalies and an LCD display to display the GUI. Moving on to the software block diagram. For inputs and outputs, we have inputs and outputs from the DSP subsystem interface. We have inputs from the timer for the rotary encoder, and inputs and outputs from GPIO for buttons and LED indicators, and the LCD for the GUI using the Touch GFX library.
Hello again. This is the audio subsystem. This subsystem is comprised of two parts, one being software and the other being hardware. Initially, the software receives a 16-bit 12 kilohertz sample data stream from the DSP subsystem. Via I2C and the serial audio interface, this initializes the audio codec. Slide. In hardware, the audio codec decodes the data to drive a local speaker. The local speaker provides voice, anomaly alarms, and the anomaly soundification that was previously mentioned.
This is our power subsystem, which is designed to power our system efficiently, consistently, and with low noise. Our input is a customer provided DC that goes through switch mode power supply to aid with efficiency. We also have linear low dropout regulators on each analog channel to assist with noise reduction, and an overvoltage protector and overcurrent protection with transient voltage suppression to help protect the system as a whole. One issue that we anticipate encountering and are working to find a solution for is going to be ground noise.
These are some of the design risks and design considerations that we've had in mind while designing our system. Now, some of these risks include delays due to the ongoing COVID-19 pandemic, delays due to the ongoing part shortages, any delays due to learning curves for any subsystem implementation, any undiscovered design flaws that we encountered during implementation, which we have allotted time for, and delays due to acts of God. We could have another Texas apocalypse, which would be terrible, but then my snowman would get a friend.
We also have some design considerations that we'll be thinking of as we continue to build this project. One of them being redundancy wherever possible, so that any small parts failures won't bring down our entire system. We also are considering size, weight, power draw, and heat generation, which is especially important for the use of this product in space and air travel. We also are considering a universal user interface by using simple symbols such as the vector described earlier to make it a little bit easier for people if everybody on the space station is using a different language. And then finally, we have our stretch goal, which is the anomaly localization.
This is our current planned milestone schedule for next semester. As you can see, by April 1st, we plan to have our full system completed and tested. And no, this is not an April Fool's joke. And hopefully by then we will also have our stretch goal of anomaly localization implemented. We'd love to give thanks to our faculty advisor / PI, Dr. Campo, our sponsor, Mr. George Salazar, to NASA and the Texas Space Grant Consultorium, to Team Aurora with special consideration to Dan Lewis and Jesus Hernandez, to Texas State faculty, Mr. Welker and Mr. Hinkle, as well as to our mentor team, Team Solar Monitor. We're now open to take any questions.
Great job. Thank you, Team Sonus. So I'm going to share my screen again. There we go. All right, so audience, please go to slido.com to submit your questions. Again, the code is TSGC 2021. In addition to questions, we're going to open up a poll for each team. If you're on, I have just opened the poll. So every team is going to get rated 1 to 5 stars. That's the thing to do nowadays, rate with stars. So we're going to give everyone a score. And at the end of the showcase, next week, we'll announce what the audience favorite was for these polls. So go ahead and rate your polls there. Let me go to the questions. All right, first question here. What microphones did you finally decide on for the MEMS array, and how big should the final design be?
We're using a, can you get that? Okay. We're using a Knowles MEMS microphone. The part number is on our block diagram. We're using it because it shows response all the way up to 80 kilohertz, although we're hoping to go past that just a little bit. How big should the final design be? We're looking to make it as miniature as possible. We found a nice development board to use for the main board, which includes all the hardware we need to achieve our primary goals and our stretch goals, although we're only going for 1 at the moment. So size should be minimized.
Okay, good. There's a comment on the patch. You want to talk about your patch design?
Yeah, absolutely. So our patch design, we actually worked with a graphic designer to help assist us with the patch. We had an idea. Katie Wilson was wonderful and made this idea into reality. As you can see, we have a shuttle that's coming out over Earth. You can't really see the Earth from us because we're blocking it. And we have sound waves coming out the back of it. Since our project is primarily focused on sound waves, we really wanted to feature that on our patch. Around the edges is our team name, along with all of our last names in alphabetical order.
All right, great. So you talked about the COVID challenges and the supply challenges. So what was the biggest challenge for you on this project so far?
I think the biggest challenge so far was getting used to being in person at school again. We'd all been used to being online for about 1.5 years. So just getting back into the flow of, all right, let's be in person, let's collaborate in person versus on Zoom with no cameras on or anything, which usually happen whenever you get put in a breakout room. So I think our biggest challenge was readapting, being social with other people other than our pets and our family.
All right, interesting. Yeah, it's great that you got together in person again. What were the supply chain delays that you experienced? I know a lot of teams mentioned that in their tag up reports.
So we personally haven't experienced any supply chain issues yet, but I know a lot of parts, especially that have to do with silicon, have been getting delayed. So we got lucky being able to get our discovery board or our microcontroller in. We may not have as much luck next semester while ordering more parts.
Mm-hmm.
All right, great. We can stop there. Thank you very much, Team Sonus. Very good. So for the next team that's on deck, that is University of Houston. So they're going to be promoted while you go back to being attendees. There we go. And let me see here. All right, close the poll. Remember, questions, go to slido.com, TSGC 2021. And to the audience in general, I just want to remind you that these teams have been working for just 2 months, really. We talk about the whole semester, but they were notified about September 13th that they were given this project, and it's just about 2 months later. And they are all going to work a second semester on this as well. So they have 7 months. They're really just 2 months into these projects. And I think they've all made amazing progress so far. All right, just trying to stay on time. It is nearly 2:30. And Texas State, if you can start your video, give me a thumbs up if everybody is here.
We're still waiting on one more. Okay. Yeah.
All right, Team 10, you are all here? All right, go ahead and share and take it away.
All right, can you see my screen?
Looks good.
Okay, Omar.
Hello everyone, my name is Omar Al-Koja, and this is Team 10 representing the University of Houston. Our mentor is Dr. Chatwin Mansdown. Our design will be for the extendable antenna mounting structure. Next, please. So our main objective is to build an extendable antenna mounting structure, and we also have some requirements for that. One of the main requirements is to sustain a minimum force of 125 lbs for 1 second. This force is given as a constraint for our team. It has to be adjustable as well. The design needs to be adjustable, meaning that it can extend and go back to its original position, since it's an antenna. It has to be automatic, so no need for human intervention, as well as it can be controlled from a space station. Basically, a programmable chip can be installed inside the motor in order for that to happen. Allow a 360 degree rotation of the antenna to cover all the area on the surroundings, since it's going to be in the moon, as well as also it will be better for communication and sustain a temperature as high as 224 Fahrenheit and as low as negative 298 Fahrenheit. That's the radiational temperature in the moon at its highest, which is about 225 Fahrenheit, and at its lowest, which is negative 298 Fahrenheit. Also, it has to have a minimum lifespan of 20 years. As we know, the space launch are costly, so by ensuring the correct material selection and the design of the device, then also we can validate by performing multiple tests on the design to see if we can sustain that 20 years, so we can reduce the cost. Next slide, please. In terms of enabling technology, we have a servo-driven gear rack that allows for extension and can retract when needed. All motors are remotely controlled, as well as there's a step motor which is attached to the gear rack, allowing 180 degrees of rotation from both sides. And this is actually very beneficial because that would allow, that would actually prevent the wire to wrap around the structure. And then the last thing would be the step motor is controlled by stepper motor driver module. And that will be it for me. And now Ismail will go ahead and introduce the design.
Hello, this is Ismail Ali. As you can see, the existing design that's available right now is that's attached to the Nova C lander. Is a very short and can carry a minimum load. Also, it cannot extend and for better communication. Next slide. So our proposed concept consists of a metal box structure with a gear rack that is driven by a servo motor, as you can see. The gear rack can extend up to 3.5 meters, making the total reach of the antenna panel to be approximately 7.5 meters by including the height of the Nova C lander. A step motor will be attached to the top of the gear rack, which will allow the antenna panel to rotate around its axis to cover all the surrounding area. The rotation will be done on 3 stages. The first stage is a clockwise rotation of 180 degrees. The second stage is a returning to initial position. And the third and final stage is a counterclockwise rotation of 180 degrees. Then the process will repeat. This is done to ensure that the wire attached to the antenna does not wrap around the structure, thus breaking. The antenna will be fixed to a rotating cylinder coming from the step motor with a cylindrical bracket holder that can be adjusted to fit the size of the rotating cylinder. Also, different types of bracket mounts are considered. Our simulation, next slide. Our simulation was done on the gear rack to ensure no large deformation or fracture occurs. The gear rack was fixed from its teeth as well as the back sides. The finite element analysis as well as the thermal analysis simulation that was performed, including two constraints, which are radiational heat of about 106 degrees Celsius applied to the whole body, which is the average temperature reached during the daytime on the moon. Also, 125 pounds of weight applied on top of on the top side of the structure, and 3.75 pounds of weight applied to the front top side, which represent the weight force that will be applied by the space crew needing to grasp or kick off the antenna structure, and the weight force applied due to gravity by the antenna panel, respectively. The weight force was applied assuming Earth's gravity, which is about 6 times larger than the moon's gravity. However, this assumption shows that our device can actually carry more than the simulated weight on the moon. The maximum deformation recorded was less than 2 millimeters, which shows that the structure will not break or develop plastic deformation for the specific type of aluminum alloy that is used as a material. As we develop the design further, we will perform more simulation to meet the changes in the device. Once our team develops a prototype, we can run more tests to validate our device. And now Yusuf will be speaking about the material selection.
Thank you. My name is Yusuf, and I'd like to first point to the antenna that we're going to be using for our device. So the antenna required for our mounting structure is a high gain type, which means it can amplify weak signals used in satellite communication. And the panels with the antenna are going to be about 476 millimeters long and have a minimum weight of 1,750 grams. And it'll allow an antenna signal of 15 dBi. So the frequency of this antenna is expected to be about 1800 megahertz. So higher frequencies, result in wider bandwidth, and that results in more higher data rates. And this will be important for facilitating the BTS, the base transceiver station, which is going to be used for LTE wireless communication. So on the left side, we're going to talk about the material selection. So in terms of material selection, we were concerned about the device becoming brittle under the moon's colder temperatures. So the moon's colder temperatures can be as low as negative 173 degrees Celsius. And for the mounting device, we found aluminum alloy T6 grade to be a suitable primary material. And it's a material that's commonly used in, heavy duty structures such as aircraft wings, helicopter rotors, and shipbuilding structures. Because it has like a very high tensile and yield strength of about 290 and 240 MPa respectively. So in addition, the alloy has a low thermal expansion coefficient of 23 times 10 to the negative 6, K to the negative 1, as seen in the table. And so that means that the aluminum alloy is going to show very little changes in elongation properties under temperatures below 0, which is very good for our device when it's on the moon. So the next table at the bottom right talks about the weight of the device. So the mounting device weighs a total of about 1,081 grams when including a wire installed through it for connecting to the antenna. The wire chosen for us is labeled as it's a model UFJ205A, and it's useful primarily for RF communications, radio frequency communications. This wire weighs about 729 grams, and it's when we translate that into pounds per feet of cable used, it will be about 0.14 pounds for every 1 foot of wire cable. So without this wire, the rest of the device is going to be significantly lighter, and it's only going to weigh about 352 grams. So, and on the table, it shows the individual components that we've selected for the device assembly. So we have the servo motor, the step motor, the gear rack, the main mounting body, panel holder, and the wire itself. So overall, you can see that the overall weight is going to be 1,081 grams. So for the discussion and conclusion, in summary, we've demonstrated the device behavior through field strain and field temperatures with a finite element analysis. And we've also went over the design concept itself to ensure it adheres to project requirements. It can be adapted to the Nova-C lander, and it's able to extend up to 3.5 meters for stronger wireless communication signals. So the next steps that we're going to take for our team is to work on making any structural improvements to our design based on the feedback that we receive. And after all the parts are obtained, we're going to order the parts first, and then we'll be ready to develop the prototype and perform additional validation experiments, and keep on improving the device on feedback and results for our antenna mounting structure. And that's it for our presentation. Is there any questions?
All right, thank you, Team 10. Let me share my screen again. Okay, so again, audience, please use slido.com to look at the questions, submit questions, vote up questions, and we also have the live poll. There we go. So the poll is open and the questions are open. All right, so first question. Let me ask about dust. Did you consider dust mitigation with your project?
Excuse me, can you repeat the question?
So with your project, I know dust is a large consideration on the moon. Did you consider that in your design?
Yeah, since actually the design rotates, and also it can, like, as you can see in the picture for the proposed concept, like it has a lot of drilled holes, which makes the design less, like, even like the debris, if the dust, like, are you meaning the debris, like something hit it,
or yeah, if dust gets into your system, like you have got a 20-year lifespan, and would the stepper motor survive 20 years in the lunar environment?
Yeah, we can actually, like, the device is like, I'm kind of showing it from the side, but it's going to be covered from all sides once it's actually finally built, because like we're still developing the device, it's not done yet, and to develop the prototype.
Okay, good. And are you going to make your prototype out of that aluminum or some other material?
Yeah, we're probably going to select the material. We actually have a large list of other materials, but we're primarily going to select that material for future prototype.
Okay, what other materials did you consider instead of that aluminum T6?
Yeah, I have a list of other materials that we have selected. For example, we have aluminum T4 as well, and titanium. We have titanium alloys, heat treated of 6Al 4B Ti. Also, we have nickel alloy of mono TD nickel, hastolide B incolide TX. We also considered different types of aluminum alloy, but actually using aluminum alloy because it's actually lighter and it can it's better for the weather at the more additional temperature that's going to affect the device.
Okay, great. Thank you. Two more quick questions. Since the gear rack was shown with FEA analysis, are the antennae movable?
Yeah, the antenna is actually movable. That's why I said that the gear rack would be fixed from its teeth. Like the motor can actually stop the gear from moving, which is actually it's pretty strong and it can carry that load, like as you can see in the simulation. But however, to actually validate the device, we will need to run actual simulation once we have the prototype developed.
Okay, and then last question online here. Have you considered the transportation of the equipment and what forces will be applied to it then?
Like, what do you mean by transportation? Like,
I guess, is the 125 pounds during operation or are there considerations during launch and transport?
no, actually, the design will be initially like at the retracted position, and then once it extend, it will be fixed at this position. And then if you want to retract it back in, you can do that as well.
Okay. All right, well, great. Thank you very much, Team 10. All right, our next team from San Jacinto College is Hyperion. Is Hyperion all here?
One more person.
All right, there we go. I think you're all here. Take it away, Hyperion.
All right, good afternoon, everyone. We are Team Hyperion, comprised of Daniel Guerra, Luis Ana Padron, Jeff Gleesman, Luis Rosario, and myself, Jordan Seibert. Today, we will be presenting the novel non-tracking fiber optic solar concentrator for extraterrestrial applications. NASA will be establishing the Artemis base at the south pole of the moon and assessing the obstacles encountered during those Apollo missions. It is crucial to consider the abrasive qualities of lunar dust that can drastically reduce equipment lifespans, design a durable source of power collection that is capable of meeting the needs for longer explorations, and to opt for materials that will optimize solar energy collection through optical and thermal means.
This year, 2 teams are working in collaboration on this project. Team Hyperion, comprised of San Jacinto and UT Tyler students, will be working on designing the lens. Team Hyperion will also be in charge of lens design, optical simulations, and thermal simulations. The second team, Team Solace, also from UT Tyler, will be focused on lens and collector fabrication, designing a testing bench, and testing for thermal concentration. Both teams working together on this prototype will then produce data that can be used to validate San Jacinto's optical and thermal simulations. Next slide, please. NASA plans to build the Artemis lunar base camp at the south pole of the moon, where there are extended periods of daylight. This base camp will need to have access to abundant sources of energy like sunlight. Team Hyperion has been tasked with designing a solar concentrator that eliminates the need for moving parts, is easily manufactured with market available materials, and can withstand the abrasive qualities of lunar dust. Hyperion plans to expand on the simulations that were run on a Fresnel lens using Optica EM, which is a program designed to run simulations of light as it passes through media. Both Team Hyperion and Team Solace have been tasked with validating these simulations in order to help provide a solid base for future projects.
Fresnel lenses have been used for a long time and can be found in many places. The most common use for a Fresnel lens is a lighthouse. In a lighthouse, the Fresnel lens takes light from a small source and projects it outward for sailors to see. For this project, the teams will be inverting the use of the lens and focusing sunlight onto a collector. By doing this, Team Hyperion can collect optical energy that will be converted into usable energy by means of solar panels. Next slide. This image shows the entire assembly and how our design will look when assembled. However, The teams will focus on fabricating a 30-degree rotation of the cylinder. This is due to the ease in manufacturing the lens and the limitations of market availability of desired materials that have the dimensions needed to fabricate such a lens. Additionally, the lens design and material selected can be easily placed into optical EM and simulated.
Jeff, you're muted, sir.
Jeffrey.
I apologize. This is an illustration of the lens in a lunar environment. As you can see, in a stationary configuration, the sun transits around the horizon on the lunar south pole. As it collects sunlight, it concentrates it, funnels it, and can be used for a variety of purposes. In this case, it can be used on photovoltaic cells to generate current. It can also be used directly to thermally decompose lunar regolith, producing O2 and helium-3 for future endeavors. Next slide.
Daniel, you're muted.
Here are the steps that need to be taken in order to successfully design and fabricate a lens. Material selection, which provides refractive index for lens maker equation and Snell's law. Sketches for optimal rib count for improved simulation time and ease of fabrication. Autodesk Inventor used for CAD drawings of lens and assembly. Thermal simulation and optical simulations run using STL of lens. CNC fabrication of lens and finished product for testing will be used to validate simulations. Next slide, please.
The lunar solar concentrator must meet key design requirements. The Fresnel lens design must be durable, modular, free of moving parts, and capable of being modified to operate at the moon. For the material selection, teams must consider having a low coefficient of thermal expansion capable of enduring temperature cycles ranging from 100 to 400 Kelvin. Furthermore, the material of the lens must have a refractive index close to 1.4 to collect most of the sunlight, and it is imperative that the materials have a high transmittance factor of at least 80% to yield a power output of 10 to 100 watts. Finally, the design of the lens and collector must withstand at least 9G to survive a rocket launch.
Team Iberia designed the lenses using Snell's law, the lens maker equation, and Fresnel loss equations. The lens maker equation is what determines the radius of curvature for the lens ribs. The input for these equations include the refractive indices of each material and the incident angles. Doing so, the convergence of light can be confirmed. When designing the lenses, it's imperative to consider the incidence angle on the collector as well. The closer the focal point was to the lens, the larger the incident angle was on the collector. To improve efficiency, the lens's focal point had to be at a distance where the incident angle on that collector is as small as possible. Fresnel loss is used to determine the S polarization and the P polarization of light. To mitigate the damaging effects of lunar dust, it was decided to apply silicon dioxide to a polycarbonate and PMMA lens. With the addition of a coating, it was important to consider the changes to the overall refractive index of the combined materials. Altering the refractive index means the focal point will shift closer to the lens. However, this shift will not be significant due to how thin the coating is expected to be.
After designing the lens, the design team transferred the STL file to San Jacinto's thermal and optical simulation branch to be simulated on Optica EM software with the appropriate refractive index that was assigned for the material. On the south pole of the moon, solar rays are near parallel to the surface. With that in mind, the team selected simulation parameters consisting of a 10 parallel ray configuration, similar to the expected angle of solar irradiance. To facilitate future prototype evaluation in an Earth environment, the primary wavelength of 0.5 microns was selected for the simulations. Orange and red rays here represent higher intensity rays converging on and entering the receiver. There was low-level intensity reflection of rays from the lens and receiver, as indicated by the blue rays. Overall, the simulations demonstrated high-intensity rays converging onto the receiver face and being funneled into the receiver assembly.
After building the ray trace simulations and confirming the efficient ray convergence on the face of the receiver, the team performed surface intensity plot analysis on the system to find intensity and energy density values. The three equations here are how Optica EM generates these results and can be explained further if there are any questions. Information about where these values came from can be found in the appendices where the codes are attached. Upon observation of the plots, the team noticed the system retained a total of 49.94 watts of energy and an increased intensity at the collector and screen faces. This data has shown that at least 49% of the energy can be retained, displaying the energy performance of the lenses. Next slide, please.
In addition to a steady state heat transfer analysis for thermal simulations were created in both SimScale and MATLAB to investigate the heat transfer of the system and attempt to predict the behaviors of each material selected. In SimScale, the heat transfer simulation solves for the temperature distribution and heat flux in solids under thermal loads. In implementing equations such as Fourier's law and Newton's law of cooling, the coefficients of each material can be found and input into the required slots in the system. After all accurate and desired coefficients, SimScale will calculate the heat transfer outputs as demonstrated on the slide, which presents us a deeper analysis that allows for inspection point tools and a summary of your minimum, maximum, and average temperatures. Parallel simulations were also run in MATLAB to ensure the outputs in SimScale were consistent. To run an analysis in MATLAB, the partial differential equation toolbox was used to provide functions for solving heat transfer using finite element analysis. The inputs for the code required that the STL be specificated to each material, the thermal conductivity, and the ambient temperature of the experimental testing site. The outputs are shown to have a slight increase in temperature distribution on both the lens and the collectors in comparison to those done in SimScale, and the code for each can be referred to in the appendices. In deciding which system is providing the most accurate outputs, comparison data with collected from the materials branch, Team Solus, needs to be done and has been added to our forward work next semester.
For power generation, the team will implement the use of a black box that isolates the system from ambient light. Within the capsule, there are multiple solar panels that are wired in series to produce up to 32.5 volts at 2 milliamps. To transport the collected optical energy, a side glow fiber optic cable was coiled and placed in the capsule. The use of the side glow fiber optic cable allows for the collected light to shine evenly along the surface of the cable, allowing for the embedded solar panels to use that light and turn it into usable energy.
In fabricating multiple testable prototypes, it is expected to validate the simulations run on Optica EM for this Fresnel lens-based novel tracking system. Once the simulations have been validated, projects can be upscaled for future lunar missions. It is imperative to consider having a modular and compact design that allows for the improvement or replacement of parts while maintaining its integrity in a hostile environment of the moon. Additionally, with the abrasive qualities of lunar dust, a system had to be designed that would eliminate the need for moving parts. Next slide, please.
And this is for our future work. We will be fabricating the lenses, a test bench. Team Solus will be using that test bench for optical and thermal concentration. We will also finish developing the power capsule to generate between 10 watts to 100 watts as usable energy. We'll also be doing finite element analysis for the lens transportation, and we'll also be testing the lens for efficiency and power generation. These are our acknowledgements for Dr. Nathaniel Wiggins, Dr. Andres Garcia, Mr. Houston Green, Mr. Christopher Mendel, Dr. Soren Maloney, Dr. Barnhart, Jacobs Engineering, and Team Solus. Thank you all.
All right, thank you, team. We have time for just a couple questions. And the first one is, the shape for the reflector seems to be very complex to machine for a glass material. Will you be using a specialized material for this design?
For the collector itself, we will actually be fabricating that out of polycarbonate and polymethyl methacrylate acrylic, PMMA. And we will be using a CNC machine. So the way it'll work is that the one side of that collector will be fabricated and then flipped on the machine itself, and then the other side will be fabricated. From there, we will move on to polishing and sanding and polishing to make sure that it is a completely clear cut.
Okay, one more question and a reminder that the poll is open at slido.com. Ask your questions and fill out the poll. What is your margin for alignment and how does efficiency drop as the source deviates from the ideal?
We do have a focal region where the collector itself will be placed. Once we started testing or calculating for the thickness of the coating, we realized that there was a slight margin where the focal point would shift closer to the lens, and that was smaller than a millimeter, so that was negligible. As for the placement of the collector within the assembly, the collector has roughly 5 millimeters that can be moved back and forth within the assembly, and it would still be within the focal point of the lens itself.
Okay, great. That concludes our 15 minutes with you. Thank you very much, team.
Thank you, sir.
Thank you.
Thank you.
Thank you.
All right, it is time for a short break. Session 1 is concluded. Thank you to the first 3 teams. Again, if you have questions, you can email us at designchallenge@tsgc.edu or go to our website, tsgc.utexas.edu/challenge. You can find the schedule there, as well as links to look at the team's videos that we showed earlier, their posters that they put online, and eventually you'll be able to watch these recordings again. So we'll see you back at 3:10. All right, welcome back, everyone. Our break is going to end at 3:10. We will start session 2 with Lamar, Team Vulcan, and then Texas Women's University, Team Leonori. Short break again, and then conclude with session 3, UT Tyler, UNT, and UTEP. So our first team for session 2 is Team Vulcan. All right, there's Team Vulcan. We had an error in our handout that we emailed out. They are all electrical engineering students, so apologies for that. And are all of Team Vulcan online, ready to go?
I believe we
are. All right. Take it away, Team Vulcan.
Hello, I am Tai Nguyen, and I am a member of Team Vulcan. So as, next slide, please. Oh, so as a member of Team Vulcan, we had the pleasure of being entrusted with the Vehicle Interchangeable Electronic Controller, aka VIEC, network system as our project design. So these are our team members, Alexander Barem, Bradley Gray, Matthew Johnson, Jordan Lake, and myself. So this is our outline for the presentation that we will be doing today. Will be the purpose and objective, criteria and constraints, initial concept and overview, time sequence and GUI, interchangeable controller, excuse me, wire schemes, and future for next semester. So moving into our purpose and objective, as humans push their explorations further into space and spend more time in deep space, logistical aspect of providing spare parts, spacecraft component becomes critical. Traveling a great distance away from Earth makes it difficult in terms of obtaining timely replacement from the safety of Earth. This has informed our objective and purpose. This brings us to our objective. The system needs to be able to work interchangeably, meaning it can serve several operating purposes. It needs to be able to configure with a network system, must have a common connector, and be able to interface with every module. Moving into our purpose, our design, the purpose of the system will be a single IC that performs various functions. This will also affect cost as having a singular IC that can be used in every application. Moving on to the next slide, criteria and constraint, Mr. Jordan Lake will take that away.
This project came with many different criteria and constraints about what we needed to simulate and how it needed to be enclosed. On the hardware side, it must be capable of interacting with 2 or more physical vehicle applications, which we can simulate, utilizing common connectors for both power and sensors, and be delivered in a physical enclosure with the sensors attached to said enclosure. Functionally, it must be able to interact with a network server, be hot swappable with a 75 or more success rate, operating 4 or more simulated vehicle applications, utilizing common serial interfaces through a central graphic showing the system's components and their statuses. Matthew Johnson will take over the initial concept and overview.
Good afternoon, everyone. My name is Matthew Johnson. I will first be discussing our initial concept and overview. Here we have a block diagram of the system that we've designed. Going from left to right, we have our network GUI, our network, and our program storage, which will all be housed on a laptop that's connected to our network switch, which is then connected via Ethernet to individually IP addressed controllers, which are then connected to their various sensors. Now for our time sequence and GUI. Here is our time sequence diagram that we worked on with Mr. George Salazar, our NASA mentor and customer. Going again from left to right, we have our data collection, which is comprised of our various sensors, whether it be temperature, pressure, etc. It takes that data, pushes it to our controllers, which is then pushed through the network to be displayed by our GUI. We have a primary and alternate loop, which is always running in the background, that will determine the health of our network and controllers and allow us to determine that on our GUI. As for our GUI, we decided to design our GUI from the ground up to meet our specific needs. Starting at the top right, we have our poll network button, which allows us to manually send a handshake through our network to determine whether or not the controllers are online. To the left of that, we have our buttons for our controllers. Once you click these, it will take you to a new page that will display the data being picked up from the various sensors on each controller and allow us to see the status of that controller. Here in the middle, we have our image controller buttons. What that will allow us to do is whenever a controller is installed in a position, we can come over here, click this button, and it will push the program for that specific controller through the network. So that way that controller will now be functioning as that position's controller. What's not represented here, but will be implemented in the future, are status indication lights. That way we can at a glance determine whether or not our controllers are imaged properly and if they are on the network or not. And from here, I'll pass it to Mr. Alex Byrne.
Thank you so much, Matthew. Good evening, everyone. I think y'all can hear me. This next section, I'll be talking about interchangeable controllers. So initially, when we started the project, we had a couple of options on deciding which interchangeable controllers, known as ICs, we wanted to use for our system. Initially, we considered on using a Raspberry Pi for its fast processing speeds, but we really didn't need the complexity of Raspberry Pis, and nor would it have been beneficial for our interchangeability needs. So eventually, we settled on Arduino boards, specifically Arduino Uno boards for its simplicity and reliability. Arduino Unos are inexpensive, open source in software and hardware, don't require any external programming, and the IDE software that comes with it can operate on any operating system, which includes Windows, Linux, and Mac OS. The Arduino Uno features several pins, such as voltage outputs, ground pins, analog pins, and digital pins. There's also a physical reset button to restart the controller in cases where a quick fix is needed. Arduino Unos both have a USB and external power ports as power sources. The USB connection allows the user to upload code to the board from a computer, but also run and loop independently, which is vital for our setup. Arduino Uno shields are separate boards that can be plugged on top of the Arduino PCB, expanding its capabilities. There are hundreds of these shields that exist, but for our case, we can utilize these ones. On the left, we can see the Ethernet shield, which can allow our ICs to connect to our network system via Ethernet and send data back and forth. On the right, we can see the CAN bus shield, which could potentially allow us to connect our ICs to sensors with an SPI interface. As previously stated, Arduino IDE is an open source software giving us an abundance of libraries and gives us the ability to ping a server. The language that's being used is called processing, which is very similar to C code. Having experience in C++, we had some areas in which we had to learn from. We tested some controller receiver code that we wrote with a temperature sensor on a breadboard and received positive feedback, which leads to my last point. IDE has the benefit of having the flexibility with most sensors. Now, this next section is going to be wiring schemes presented by Bradley Gray.
Hello, my name is Bradley Gray, and I'm going to be talking about what is going into our decision-making process with the wiring scheme between the IC and data collection. Our first look at wiring starts with the OSI model, mainly the physical and data link layers. The wiring scheme will require both digital and analog signals per the constraints of the project. And when choosing a wiring scheme, we first consider distance, how far away the data collection can be from the IC, usability, how easy the wiring will be to learn and implement, wire amount, 2-wire, 4-wire, or dependent on the amount of sensors, and interchangeability, how easy it would be to create modularity with different sensors and simulators. Here's a chart I created showing 4 different wiring schemes: I2C, SPI, RS485, and CAN bus. This is not an exhaustive list, and in the coming weeks, we will be examining more wiring models to choose the one that will operate best for real-world conditions. All of these schemes do encompass the physical layer, but they do not all encompass the data layer, so that is also another thing to consider. Moving on to section 7, the future of the project, presented by Jordan Lake.
Moving into our next semester, we'll begin integrating the systems we've designed this semester using our functional block diagram and begin the simulation of these sensors and testing of the system to ensure it meets all of the requirements stated by our prompt. Construction of the physical hardware and enclosure will follow this, proving that these simulations operate correctly. And then I would like to thank our professor, Dr. Takaz, Dr. Tim Urban, and our NASA mentor, George Salazar, for helping us in this process.
All right, thank you, Team Vulcan. So audience, if you would, go to slido.com, ask your questions there, take the poll, use code TSGC 2021 to enter the poll and the questions. Let me ask a question. Back in your requirements, it said a 75% success rate for being hot swappable. That seemed kind of low to me. I guess, what are your take on that percentage?
The percentage was laid out in the prompt itself. It seems like a fairly low bar to reach, but it was the one stated.
Yeah, I imagine that for our project, we're going to try to achieve 100% interchangeability, but I guess there are certain cases that may arise in our process of completing this project where interchangeability with every single controller may not happen. But of course, the goal is to have 100% interchangeability.
There was also one more constraint I wanted to talk about, which was 20 seconds for the hot swap. So if we were not able to reach the 20 seconds, I think we would consider that a failure and then rethink the code. So that may affect the percentage.
Okay, and so then do you think this would eventually be usable for critical systems, things like life support, or for now, is it non-critical systems?
Until we can prove that the success rate is far greater than the stated goal, I believe it would be mostly for non-critical systems.
Okay, good. We have a question on Slido. How do you plan on applying the OSI to a CAN bus implementation?
There are the shields that we can use for that. It's not like we've chosen CAN bus as a solid solution yet. We're still looking at, and that's kind of been a lot of my job, is figuring out all the different models and different ones that we can use. CAN bus is an option. It's one that was actually presented by one of our professors that we worked with. Although we're still kind of looking at it and making sure that we choose the right one that would apply. I know that CAN bus is used a lot in vehicles, and that could work in this application, but we don't want to corner ourselves into problems later by choosing inaccurately now.
Okay, thank you. And next question, why aren't you using a dual redundant system as part of your design?
Yeah, I'd say that's a good question. It's definitely not something I thought of before. And I think for sure we could think about that and, figure out how we could, reuse that. We'll definitely talk with George and see per his requirements, since he is kind of the person we like to bounce off of and say, what are the areas that you are looking at most? I know for us, he has said, just as a customer, that the biggest thing he wants to see is hot swappability. So the rest of it isn't as important to him. But if that were something that he was most interested in, then that would be something we could shift our focus to.
All right, thank you. Next question. What is the bandwidth communicated between the data collection and your GUI?
We haven't finalized a specific bandwidth that we're going to use yet. Once we have a final working product, we'll be able to determine more accurately what the bandwidth requirements are. We don't want to kind of box ourselves in to a limitation to where we'll start losing stuff on the network because of a specific bandwidth that we try to set out and pursue.
All right, great, thank you. And finally, let me ask, what was your biggest challenge working on the project this semester?
Likely the remote aspect to this. None of us are really on campus and multiple of us are off campus entirely. So finding time between ourselves has been a bit of a challenge for this semester.
Yeah, I think also just to kind of reiterate is none of us have really had a significant amount of experience with looking at things like RS-485, CAN bus, and that's a big learning process, and it's something that we're kind of looking at head on, trying to inundate ourselves as much as possible because I work in an industrial application where I see RS-485 a lot, but you don't ever get to the design section of RS-485. And in terms of that, it's usually just done already and you just have to implement it. So that would also be a big thing, I think, for sure.
And yeah, just to reiterate, one of our biggest challenges is selecting our future wiring scheme for our data collection between the ICs and the sensors. So that's going to be one of our biggest focuses in these upcoming weeks. And of course, working remotely, as Jordan had stated earlier.
Okay, great. Thank you, Team Vulcan, and look forward to seeing how your project progresses next semester.
Thank you.
Thank you.
All right, next up is Texas Women's University. I believe everybody is online on one channel. Is that correct, Natalie? Okay.
Yes. Sorry about that. We had to make sure our camera and mic were working.
No, you are good to go. So take it up, Team the Oneri.
Alrighty. Let's see. Can you see our screens or our presentation?
Looks good.
Okay, wonderful. Then we'll go ahead and get started. Okay, good afternoon, everyone. My name is Natalie Wilkinson, and I'm the team lead for Team Oneri. My team members are Melanie Meek, Andrea Martinez, Casey Rice, and Andrea Kim. Together, we represent the School of Health Promotion and Kinesiology at Texas Women's University in Denton, Texas. Our faculty mentor is Dr. Rhett Rigby, and our NASA mentor is Dr. Benjamin Easter. We will begin today's presentation with Melanie, who will be discussing background information related to circadian rhythm desynchronization. The circadian rhythm is an internal process of the brain that regulates the sleep-wake cycle. Outside environmental factors can affect the circadian rhythm, such as lightness and darkness. In microgravity, astronauts witness the sun rise and set about 16 times per day. As a result, a disruption or desynchronization of the circadian rhythm may occur, with some astronauts reporting to be less alert and unable to sufficiently complete tasks, which is especially problematic during extended spaceflight. There are several strategies that NASA is currently using to mitigate the negative effects of circadian rhythm desynchronization. Sleep medications, many of which are hypnotic drugs, prove to be the most popular option. Hypnotics typically improve sleep quality and duration, but decrease mood. Other side effects include headaches, dizziness, drowsiness, and visual problems. Another countermeasure is caffeine use, and the adverse side effects of this central nervous system stimulant are well known. Sleeping bags are also used by NASA to combat lack of sleep, but most sleeping bags are reported to be uncomfortable. NASA also utilizes the solid-state lighting assembly. Installed in 2016, the assembly aims to improve circadian rhythms in astronauts. Solid-state LEDs with adjustable colors and intensities replace fluorescent light bulbs in the interior lighting system of the ISS. This assembly currently uses 3 settings. One of these settings is a higher intensity blue-enriched light to elicit feelings of alertness and shift circadian rhythms. However, astronauts cannot experience personalized light therapy since the lighting system is shared, and circadian rhythm desynchronization remains prevalent. Also, the assembly is expensive and challenging to maintain. While astronauts may not have a personalized light therapy protocol on the ISS, individualized light therapy treatments have been successful on Earth. For example, bright light exposure is a practical way to reduce jet lag. Light therapy has also been implemented with individuals who suffer from seasonal affective disorder, which results from an extended amount of time in extreme environments with limited sunlight. Finally, light therapy emitting blue wavelengths of light decreases daytime sleepiness and promotes alertness, which in turn positively affects cognitive performance on Earth. According to previous published research, we found blue wavelengths of light are more effective in increasing levels of alertness and cognitive performance compared to other colors of light. Now, here's Casey to discuss the problem and solution for our design.
The problem that we faced was circadian rhythm desynchronization and microgravity, resulting in decreased alertness and cognitive performance in astronauts. Our solution is glasses emitting blue wavelengths of light via LEDs strategically located on the frames peripheral to the eyes. Next, Andrea will discuss the components of our prototype.
This slide demonstrates a graphic SolidWorks rendition of the components we used in order to build our light therapy glasses prototype. These include 8 blue LEDs, with 4 shown here, a USB nylon-like poly charger board, inductive charging composed of copper wiring and a charging board, an on and off switch, LiPi lenses with holographic tape and a black foam piece attached, a lithium-ion polymer battery, and an Arduino Nano board. Here we can see how the components mentioned were assembled for our prototype. We would like to highlight a few components now. The 8 blue LEDs can be found attached to a board superior to the eyes. The on and off switch is on the outside right of the lens frame, right behind the Arduino Nano board, found on the same side. And finally, the lithium-ion polymer battery is located on the inner left of the lens frame. Now back to you, Casey.
The goal throughout the design of our device was ease of use, portability, personalization, and effectiveness. The light intensity of the LEDs used is approximately 1,000 lux with a wavelength of 468 nanometers, which corresponds to a blue color within the light spectrum. These values were specifically chosen for the optimal combination of light and color for alertness. The capacity of the lithium-ion polymer battery is 350 milliamp hours or 1.3 watts. When fully charged, the battery can sustain a total of 8 light therapy sessions, with each lasting 30 minutes. Our wireless charging component was chosen for convenience and draws approximately 500 milliamps. The total amperage draw of our prototype is 0.35 amps. We developed our code to not only turn the light therapy glasses on and off, but to have an automatic shutoff upon completion of light therapy. Once turned on, the light therapy glasses will run for 30 minutes. We chose the Arduino Nano and the C++ code because it is most user-friendly and easiest to use for the beginnings of the prototype and code development. On the right, you can see the wiring diagram that correlates with the code used. Pin code 3 is for the LEDs, pin code 6 for code function, and pin code 8 is for a vibrational component that will be added to the glasses in the spring. Now, here's Andrea to discuss our methods of testing.
Before our testing protocol began, our participants had to emulate the sleep schedule of an astronaut. This included the strict adherence to 6.5 hours of sleep every night, the week before and during testing. In order to reduce outside influence on our testing results, our participants avoided caffeine, naps, and sleep-inducing medications during this time. Baseline measures were taken before light therapy, immediately after a 30-minute session of light therapy, and 1 hour after light therapy. These measures included electroencephalopathy, or EEG readings, and results from the psychomotor vigilance test, or PVT. An EEG is used to measure the electrical activity of the brain through the depiction of various waves. There are 5 brainwave types: alpha, beta, delta, gamma, and theta. Decreased amplitude and increased frequency of beta waves are associated with greater levels of alertness. Thus, this is the waveform we focused on. For our protocol, 20 total electrodes were used. 4 of these electrodes were placed on the frontal lobe, which is where beta activation is most present. As you can see on the slide, we selected 1-second epochs from the raw data. Our analysis concluded that wave morphology did in fact change after light therapy was administered to a more jagged shape with low amplitude and high frequency as seen in beta waves. The control waveform and the waveform measured before light therapy exhibited greater intermixed frequencies of lower value. The other measure that was assessed was the PBT, which is used to measure participant alertness and cognitive performance through a reaction time test following a displayed visual signal. A low overall reaction time is indicative of greater levels of participant alertness. When light therapy treatment was administered on test days, both participants exhibited faster reaction time responses when compared to the control day when no light therapy was performed. BL is baseline, which was before light therapy was administered. T1 is the test immediately after light therapy, and T2 is 1 hour after light therapy. This supports our theory that following light therapy treatment, a participant will experience faster response times and greater levels of alertness both immediately after therapy is administered and 1 hour later. Now, here's Natalie to conclude our presentation.
In conclusion, circadian rhythm desynchronization can cause reduced levels of alertness and poor task performance in astronauts. Based on our research, one of the best methods to retrain the circadian rhythm was through light therapy intervention. This option is preferred amongst other strategies currently used because it is safe, non-invasive, and most convenient. Our light therapy glasses are advantageous in particular because it is cost-effective, offers individualized protocols, and is small and portable. It requires a minimal amount of power to operate and has wireless charging capabilities that offer convenience to the astronaut. There are future considerations that can be noted involving our project design that may further enhance its effectiveness and usability. The first is the implementation of a code that allows for various light therapy durations, therefore allowing for flexibility of therapy around astronaut-specific schedules. Another future consideration is the addition of various LED colors into the device. Although we found that blue light was the most effective in stimulating alertness, other colors could be added to aid in the promotion of sleep onset. We would also consider the addition of vibration, signaling the end of a session of light therapy. We have already accounted for this in our code as seen earlier in this presentation. Here are the scholarly articles that we referenced in this presentation. Here are our acknowledgements for the project. Finally, are there any questions at this time?
All right, thank you very much, team. All right, audience, please go ahead and go to slido.com. Use the code TSGC 2021, and you'll be able to ask your questions, enter them, and answer the poll. All right, the poll is open. First question here. Did you consider lamp radiance or irradiance limits for eye safety, and how did this impact your LED selection? The comment is, blue light is more hazardous for retinal eye hazards.
So we did extensive research on whether or not a particular light intensity and also the wavelength that is used would be safe for the eye. We also tested with an individual, one of our participants also had a sensitivity to light, and it actually did not affect her subjectively in any way at all. In our research, we saw up to 10,000 lux, and with the most consistent range was at approximately 1,000 lux of an intensity of light.
Okay, thank you. So yeah, I wanted to ask about blue light. If you look up, if I just Googled blue light sleep disorder, it would say, don't look at my phone at night. So is this kind of the reverse? Is that in the morning you want to look at blue light?
So based on the research, we found we actually want to elicit alertness in astronauts, since one of the relevant issues that astronauts face in space, it's actually listed on the NASA database, is circadian rhythm desynchronization, which causes reduced levels of alertness and inability, or they're not able to efficiently complete their task. So with using blue light therapy, it should promote alertness and hopefully help them complete tasks better on the ISS.
Okay, is this something they would wear while they're working, or would they have to stop what they're doing and put these on for half an hour?
So we design the glasses so they can actually wear them while they do tasks on the ISS. The light is located at an angle to where it does not directly penetrate the eye. Therefore, they're able to, as you can see on Casey, they're able to do tasks. We strategically, there are, one of the parts of our design is we redistributed the components evenly throughout the frames. So the weight is evenly distributed. So if she were to bend over to do something, whether that's a task on the ISS, pick something up, whatever it may be, her glasses will not slip off her face. So it's actually pretty comfortable, according to the participants who were in our study.
Very good, very good. Last question here. Oh, that's interesting. So would it be possible to construct an AI routine to analyze your EEG waves? Maybe to have it tell you when you're done before the 30 minutes.
Well, for EEG, so what you're supposed to do is it's between 16 and 20 electrodes. And then you have to scoop a paste on, you have to part your hair all different ways. So using an EEG may be a little difficult with the AI, but if you are connected to an EEG and there is AI connected, I would say that you would be able to do that.
All right, great. Oh, we got another question here. Would the zero gravity make it float off your face? Is there anything to attach it to your head while you're using it?
So in our future considerations, we've actually implemented that as one of our future tasks that we would encourage the spring team to do. Since right now we basically made the base model of the project. So in the future, we would like to add a strap that's connected towards the end of the lenses that considers for that.
Okay, great. All right, thank you very much, team.
Thank you.
Thank you.
Cheetah.
All right, that concludes session 2. We'll take a quick 10-minute break and be back for session 3 with UT Tyler, UNT, and UTEP. See you in 9 minutes. All right, good afternoon and welcome back to the TSGC Design Challenge Showcase. We are about to begin session 3 with UT Tyler, UNT, and UTEP, our final 3 teams. I want to remind our audience, you can go to tsgc.utexas.edu/challenge. That's our website to see the full schedule. You'll be able to download our program and access to links to view the team's videos, presentations, and virtual posters, and also have links to provide feedback, which we are soliciting through next Sunday. So if you can, look through those materials and provide feedback for the teams. All right, first up with session 3 is UT Tyler's Team HEC 7 Callisto. Again, audience, please use slido.com to submit your questions. Use the code TSGC 2021. And that is the way for everybody online at YouTube, as well as on the Zoom webinar, to submit questions for the team. And we'll have a poll to give the team stars after their presentation. So Callisto, are you all here and ready?
Yes.
All right. Take it away. Should be able to share.
Hello, we are Team Callisto with the University of Texas at Tyler, and welcome to our presentation on our EVA sample size location calibration marker. We are sponsored by Marker G Next in addition to the Texas Space Grant Consortium. On the team, we have myself, Christian Pirucci, the team lead. We have Kirill Nikolov, the deputy team lead. We have David Rubio as the communications lead. Anthony Melgar is the research lead, and Mercedes Cedillo is the treasurer. And we're mentored by Dr. Mohammed Biswas from the Department of Mechanical Engineering. So we will begin our presentation by going over some relevant background to our project. We will follow up with the design specifications and then introduce our proposed design, which is our compliant EVA sample marker, which is to be used for the upcoming lunar landing missions. So the purpose of our project is to design a safe and easily operable sample marker to be used by astronauts for the identification process of lunar specimens. Additional considerations such as our marker being reusable, having a photometric reference chart to help identify specimens, and being able to withstand the lunar environment are all going to be considered. So the upcoming Artemis III mission set for 2024 will be the first human moon landing since the 1972 Apollo era mission, in which astronauts will be tasked with collecting geological specimens to deepen our understanding of the lunar geology. And prior to being collected, these specimens will be identified with devices such as our proposed marker. So the identification procedure consists of a sample marker being deployed on the lunar surface next to a lunar specimen, after which a photograph will be taken of the marker next to the specimen. The photograph is then transmitted to Earth-based scientists who will use the photometric reference in order to identify the physical and potentially chemical properties of the specimen and determine whether it should be brought back to Earth for further analysis. So our proposed design will attempt to alleviate some of the design faults associated with the previous era sample marker, such as the potential safety concerns, the strenuous deployment, and the high demand for dexterity it previously had. So photometric references are an integral and very important component in the identification process of these specimens, since the different colors provide an overall abundant and a very important amount of information about the lunar geology. And with that being said, I will now pass it off to Kirill, who will introduce the design specifications of our project.
Thank you, Christian. For the design specifications, we categorize them into 3 different categories, and they are quantitative, qualitative, and safety. And shown first here are the quantitative selection, and the main specifications from this category include having a maximum weight of 1 pound for the marker, a maximum volume of 2 inches by 4 inches by 15 inches when the marker is stowed, having it be independently stable on both flat and inclined surfaces of at least 20 degrees when it's deployed on the lunar surface, and having a photometric identification reference chart to be visible somewhere on the marker, which consists of red, blue, green, white, black, and gray color blocks. Our qualitative specifications include having unique alphanumeric identification labels for each marker to tell them apart from one another, having the marker be deployable and retrievable with only minimal bending and interaction being required, having a flight-like material composition for the marker so that it can properly withstand the lunar environment, and having a manual deploying mechanism for the marker which does not contain any electric components. The safety specifications required our greatest consideration, and they include having a minimized number of pinch points present on the marker, and if these pinch points cannot be completely eliminated, they will be visibly marked with warning labels. In addition to there being no sharp edges whatsoever at any point on the device, as well as no holes or openings large enough to entrap fingers. And this is Team Callisto's compliant EVA sample marker shown in action on the lunar surface in both the deployed and stowed positions relative to an average-sized astronaut. And over the course of the next several slides, we will go over in detail how the marker will operate and how it will function in accordance with the design specifications. And with that, I will pass it on to David.
Thank you, Carol. As we can see here, our compliant EVA sample marker will be designed with the use of compliant mechanisms, which are flexible structures that are designed to have components which can achieve motion through elastic deformation of adjacent components, such as plastic belt buckles commonly encountered on backpacks. Our compliant mechanisms will be in the form of tripod legs to stabilize the marker, and the legs will fit into a compact cylindrical tube, and the legs will be deployed out of the marker by simply flipping it over, which will cause a heavy ball to push the legs out to help with gravitational force. Since the legs are flexible, that would allow them to elastically deform and take shape on flat and uneven terrains while maintaining stability. The marker will also have a photometric color chart wrapped around the main body for a full 360-degree field of visibility, and will be manually deployed by the flipping motion. And the compactness of the design will allow it to fit within a 2 by 4 by 15-inch volume, and the overall height of the marker when it's deployed, which will be about 20 inches tall, will allow it to be placed on the ground with only a small amount of bending being required, typically about 2 to 3 inches of bending at the waist or the knees. The total weight of the marker will also be around 0.84 pounds, using flight-like materials and the size of the main body, which will be able to fit comfortably in an EVA glove. The maximum grip force necessary to hold the marker with standard EVA gloves is only 0.6 pounds, which will allow it to be easily operated by any user. The unique alphanumeric identification label will also be displayed below the photometric chart. A lot of analysis was performed on the marker using AutoCAD and SolidWorks to determine what the stability of the design would look like. And based on our simulated results and taking into account the flexibility of the legs, we expect the marker to be able to remain stable on inclined surfaces of up to about 35 degrees. In simulations performed on the stress and strain occurring on the flexible joints of the legs when deployed on the surface, allow us to determine that these stresses and deformations would not cause the legs to buckle or fail. Now I will pass them on to Anthony, who will go into more detail about our testing procedure and safety features.
Thank you, David. As we can see here, the testing procedure of the marker will be accomplished in 5 steps. The marker will be stowed on the astronaut's tool belt, like shown on step 1, and the user will grip the marker in the indicated location to detach it, and will flip it over to allow the deploying process to occur. Then the marker can be gently placed on the ground to minimize the amount of dust which is kicked into the air. Once deployed next to a specimen like in step 5, a photograph can be taken of the sample. As mentioned by Kirill, a lot of consideration was given to the safe operation of the marker. We were able to design our marker so that there are no sharp edges located anywhere on it and no pinch points, as well as no way for the astronaut's fingers to become entrapped while operating the device. Here we can see the risk assessments for each of the specifications, and overall the marker is currently able to comply with each design criteria except one of the minor specifications, which is to build 5 physical prototypes. But this is a low risk factor since building 4 more prototypes in addition to the first one is an easy task. Moderate risk factors are associated with the stability and weight specifications since our results are based on simulated data and mathematical models, which may vary slightly in regards to how the design will physically function. However, the simulated results still show that we will have a large margin of safety to work with, even if they are not 100% accurate. Our future direction for the project is to begin the manufacturing process, which we have scheduled to start on November 29th. We will be utilizing two sets of materials. One will be specific for 3D print prototyping at the Neutral Buoyancy Lab located at Johnson Space Center, and the other is for flight-like considerations during actual moon landing missions. Since using flight-like materials can become very expensive, initially prototyping the marker with more accessible materials and components will allow us to simplify the process, and we will be able to generate more results in less amount of time before finally building our final flight-like marker. And now Mercedes will finish off her presentation by going over our budget and conclusion.
Thank you, Anthony. This table outlines the estimated budget for our project, which consists of materials for prototyping our marker and other physical aspects of the design, including manufacturing costs and traveling costs during participation in the Micro-G workflow next semester. The source of these funds will be our involvement in the design challenge, and the projected cost of our marker will be approximately $40.39 for a non-flight prototype and $128.55 for an actual flight-like marker, which can be usable on the lunar surface. These are a technical reference used for our presentation today. And this concludes our presentation. Thank you for watching.
All right, thank you very much, Team Callisto. Okay, audience, please go ahead and go to slido.com. You should see a poll there, as well as questions that you can upvote or ask. We have a question here already. I guess it relates to the color checker marks. I don't know if those were provided to you or if you have input on those, but the question is, have you tested your color checker marks with cameras under different lighting to prove color correction usefulness of the color selected?
We have not currently tested the colors, but that is a very good piece of advice for us to incorporate into our future plans. Thank you for that.
Okay, next question. How can we be certain that the marker will not tip over on an incline, and how was it calculated?
That's a great question. Thank you for asking that. So the tipping point of the marker was determined by calculating where the center of the gravity of the marker would be, as well as where the points of contact would be. So since our marker is in the form of a tripod structure for the legs, there will be 3 points of contact with the ground. And when we look at the location of the center of gravity relative to those 3 points of contact, when the center of gravity is located above the tipping edge of the marker, which in our case would be at the lower end of the incline, where the lower legs have a point of contact with the ground at the lower end of the incline. When the center of gravity is directly above that point, which is called the tipping edge, then toppling will be imminent if the center of gravity was to go further over that edge. And that's because the force generated from the weight of the marker pulling it down, once it goes over that edge, then it'll start bringing the entire structure down, kind of like in a rotational motion over the toppling edge. But as long as the center of gravity is on the other side of that particular edge, then it will be stable. And our simulated results for a 20-degree incline give us, I believe it was a 1.73 factor of safety for toppling, meaning that we're about 1.73 times as safe, basically, for like a 20-degree incline. And as mentioned, I think we can go up to about 34.64 degrees. And 34.64 degrees will be that specific point where toppling would be imminent. And anything more than that would cause the marker to pretty much tip over.
Okay, and then follow up from me. Did I see that the legs were different or are all three the same?
So some of the legs were drawn a little bit differently. That's because we have different variations of the legs. And our purpose is to have, at the moment, we currently do have several different variations of the legs, which we plan on prototyping each leg and comparing an aggregate of the data and performance based on each set of legs to see how the flexibility functions, for example, or how good it is at maintaining stability on inclined surfaces. And then based on the results we get from that data, we will move on to our final flight-like prototype of the marker based on those results.
Okay, next question. Do you think the support of the device is sufficient, what prevents the legs from bending all the way to the ground?
The support of the device is sufficient. The way that the compliant mechanism is functioning is that under a specific amount of force, the material is going to deform a specific amount. That amount we can calculate through both SolidWorks and numerical analysis. And depending on the gravitational force and about the distance, which is about 2 inches that the marker will be dropped onto the ground by the astronaut, we can find the forces that are going to be exerted on the model and then decide the thickness or the material that we're going to be using for the legs and decide what thickness is required to perform that specific deformation that we want and have the material be rigid enough so it doesn't immediately fall over, but flexible enough to make that small changes in height.
Okay, that leads into the next question here. Would the user have to kneel down to pick up the device, or how tall is the device when deployed?
So for that, the device itself is 20 inches tall whenever it's fully deployed. And so by having that, we counted it for a 6 foot tall person, they would only have to bend about 2 inches at the waist. So it's not that big of a bend, and they can grab the top of the tube and then flip it over.
Okay, and last question here. Will dust in the environment picked up as the astronauts travel impede the compliant mechanism?
So dust will not impede the compliant mechanism because the compliant mechanisms are in the form of legs, which are attached to a type form fitting, which we showed in one of our slides, but I don't think I can navigate back to there. But basically, it's a cylindrical shaped fitting, and the legs will be attached to the bottom of it. And this cylindrical shaped fitting will be tight fit inside the tube. So basically, this fitting will slide through the tube to deploy and then also contract the legs into their deployed and contracted position. But it will be tight fit to the point where dust will not be able to enter inside that internal component or internal compartment. Excuse me.
Okay, great. Thank you very much, Callisto.
Thank you for your questions.
All right, next up, we have UNT and the cleverly titled, untitled team. Are you all here?
Hello, yes, we are here. Just 1 minute.
Okay. So reminder to the audience to go to Slido. You can fill out the poll for the last team and ask questions for the current team.
Let me just share the.
All right, UNT is going to present on their advanced spacecraft lighting control system.
Okay, are you able to see our screen?
I see your screen. I guess just go to full screen so we don't see the edges there.
Awesome. Hello, my name is Ali Hamoud and I'm the team leader for Team Untitled. Our project this semester is going to be Advanced Spacecraft Lighting Control System. And so we're going to start by talking about how we thought about this thing in the first place. So in space, crew members will not be able to maintain their circadian rhythm. So we are creating a method to help them maintain that. And in addition to maintaining the circadian rhythm, we are also going to make a profile to help grow plants under certain lighting control conditions. There's going to be a secondary goal that hopefully we'll be able to maintain for the system, and which is going to be voice control and voice commands. We're having an ecosystem of a Raspberry Pi to monitor the entire system. We will have a main Raspberry Pi as acting our server, and the other Pis to send and receive information. A touchscreen LCD will be used to communicate between the user and the server, and different users will have different profiles each assigned as a crew member, administrator, or a troubleshooter?
So we have designed the system to have their own individual parts. One big benefit for this is to have, if one part is malfunctional, then the rest of the system will still be operational. So that way you can replace the part and make it a simple fix. So it adds a sort of layer of redundancy just in case in the event of an accident. Also, having a main server sends out the information to the rest of the other microcontrollers, which makes it streamlined and frees up resources for other sorts of data. So the hardware block diagram shown right here will show about how our system is going to take place. And we will have one microcontroller per system to prevent any other microcontroller, and allows room for expansion if the need arises. So as for the lighting system, how it goes, each Raspberry Pi will have both a lux and RGB sensor that will be connected to one Pi, and the information will be split into the server. And then the profiles will be loaded. We'll select which color for the profile and output the light to the light bar. The sensors will also monitor for degradation and compensate if the lux drops.
As for the central control, will go as follows. It's going to be basically our main control system, and we're going to be using Android Studio to design the central control system that can be run on any Android platform, that being a tablet, a phone, or our home-built Android Raspberry Pi. The app will be connected to the servers using Retrofit and exchange data as needed. The main screen will show the control options, which are listed as follows. We're going to have lights, rooms, profiles, sensors, plans, and troubleshoot. We're going to have the ability to add or remove any of those components as needed. So if we need to add a new light or add a new room, assign different profiles to it, or even assign a plant profile, which monitors how the plant is going to grow and provide with the necessary lights. And at the end, a troubleshoot is going to run all the possible commands and test the connections to see if everything is working as needed.
So the server and networking will fundamentally function as follows. There'll be a central controller that the front end lights and sensors will communicate with. This will be running on a Raspberry Pi, as all of our other sensors will, just to simplify the implementation. The controller will then connect to the sensors and lights over the network using a host name, which will be configurable through the GUI as part of implementing and adding those sensors or removing them. This controller will hold the system state as a whole and provide a REST API interface for the GUI to interact with, as well as the lights and sensors to communicate with. And then the controller will also monitor for degradation and send out the circadian rhythm on schedules. So for our preliminary results, our UI has already been created with a limited functionality. Here's a preview of it on the side. And our main server has been successfully set up and is sending and receiving information to and from this UI. Our light control is not fully functioning yet, but we think we have a way to work it out in a good cohesive system. So for our schedule, today at the top is our preliminary presentation. Our semester ends on 12/6. And then over the winter break, we will continue working on this project, and our semester resumes on January 10th. From there, we will finalize our project on the 25th of March, and on the 8th of April, we will present.
So in summary, we are currently on track given our current schedule, assuming there are no other external issues to arise. As the government shutdown is pushed back to December, we don't know how that will affect the NASA budget and or any other external factors. Also, same thing with lead times for certain parts. Currently, as it stands right now, our project is about 45% complete at this moment, and we're doing our due diligence to keep track of our given schedule and maintain accountability for our respective sections. These are our acknowledgements here. We have Dr. Robin and George and Dr. Tim Urban, our lab manager and architect for our designs, and as well the UNT department. Do we have any questions?
All right, thank you, team. Let me open the poll here. And people go ahead and ask questions. Okay, we've got a question already. Have you thought about scalability, parentheses, the number of channels or lamps or zones? And have you looked at ArtNet and DMX 512 topology to help you with ideas on your design?
Yeah, so I'll start off with the scaling. Our system is designed as a rather POC. To fully scale the system out, we would work with a redundant controller-based architecture. So each node could become a controller in the event of failure. For our implementation right now, we have a centralized controller because implementing that would probably take too long to be reliable. So that's in regards to scalability, that was our plan. And for DMX 512, I'll let Alex go ahead and take that because he's been handling our lighting stuff.
So for the DMX 512s, we do have a API that can be able to easily transmit, send, and receive data from a server to able to change colors as well as other information needed. So all it is just setting up another profile for that specific light and then just adding that into kind of our little bank of sorts of just profiles. So scalability should not be a huge issue in the future.
As also for the control itself, the UI already have implemented the ability to add or remove lights, sensors, and rooms. So it accounts for any issues we would face while scalability. So in case if we want to scale into more rooms or add more lights within the same room, that is totally possible.
Yeah. I do want to be clear. When I was referring to scaling, I was referring to tens of thousands of scales, not like units, not 1,000. We're using REST API architecture, which should scale very linearly with resource usage.
Okay, all right, great. Great, and next question. What color spectrum wavelengths will you be using for the prototype?
So since our case is kind of unique, we have a plant profile, which is going to, depending on the type of plants that we're going to be growing with, which more specific is going to be quick growing plants like tomatoes, things like that. So we're going to be using green lights and red lights to help accelerate from what I've seen online. And as for the human profile, it's tying to a circadian rhythm. And we're going to be using warm lights for the morning portions, for the day portions, and then cooler lights at the night portions to help simulate a transition throughout the day.
Okay. What were some of your biggest challenges? I know you mentioned things that might be upcoming, but technically, what was the biggest hurdle?
Our biggest hurdle was the hardware, the supply issues. That's really about it because it's taking time to get all the components we need, especially right now that we aren't able to order more than one Pi at a time, and it's hard to find any in stock. But other than that, everything been going pretty smoothly.
Good. That's good to hear. And I guess you can meet in person since you're all together there.
Yes.
Yeah. That's very good. Is this the first semester you've been back together?
Technically, so last semester UNT did a hybrid. So half the classes offered in person or online. So it was up to the students to either go to one or the other. So, but this semester they kind of full in person.
Yeah, we're required to be here.
Yeah, this is the first class in person for me since a while.
Yeah. Very good, very good. And then who came up with the team name?
So the team name, we kind of collectively came out with that. Honestly, we're sitting here. I was like, what are we gonna do? What are we gonna name? And I was like, have you guys played Untitled Goose before? And let's just go with that. And we capitalized the first few letters to account for the UNT kind of part of it. And that's how it was formed.
It's perfect, yeah.
Thank you.
Yeah. So next question, how do you plan on testing or proving the circadian alignment?
So this kind of goes along with so a lot of issues aside, I have a bunch of severe sleep insomnia issues. I'm also going to see sleep therapists, sleep doctors, so on and so forth. I'm trying to get this all taken care of. So I'm using the information that I'm gathering from that, what they're doing to me, and just kind of putting that into like a data set spreadsheet, and then just taking that information and just crunching it into the server and seeing where is a perfect balance point for all of this to kind of make a lot more sense.
So we're gonna make like timetables based on the sleep schedule and like how we functioned throughout the day for each of us. And we're gonna be using basically ourselves as the test subjects. If we try this at home and we're able to sleep, then it works. If not, then we need to fix it.
All right, good. Well, good luck next semester. Thank you.
Thank you. Thank you.
Okay, our third team in session 3, final team for the afternoon, is from the University of Texas at El Paso, team MME. And we're doing a bit of time travel here. You're in a different time zone, an hour earlier. So hello over there. Are you all ready?
Oh. Hello, we are ready.
We're ready.
Can you hear us?
Okay, we can hear you now. Yep, you're good to go.
Okay, perfect. In our end, we got the dark matters project, which is talking about how a black body would help absorb radiation coming from cosmic rays and the solar rays. We have from right to left, Hugo Heredia. We have Hector Samarripa. Hello. Cassandra Orozco. Hello. Daniel Morales. And myself, Kevin Rendria.
All right, sorry to interrupt. Could you put it on full screen so we can see the whole thing, please?
I thought I had it on full screen. Let me try again. I apologize. Okay. Share screen. This one. Is this better?
We still see the all the bits around the slide. Make sure you're in presentation mode. And make sure you share that screen.
I am selecting slideshow.
Yeah, go ahead and stop share, and then when you select the screen to share, make sure you're selecting the full screen presentation.
Okay. I select share screen and then screen 2. Is this better?
That's perfect. Thank you.
You're welcome. Human exploration has thrived throughout history. We've discovered new lands, new seas, and nowadays we are exploring the space. Research conducted by NASA has led to believe that there's ice water present in the south pole of the moon. There's structural as well as environmental challenges. We know that in the south pole of the moon, we have one of the coldest temperatures that we have in our solar galaxy. So in relation to manufacturing processes, architectural and material selection applications, our theme, Black is Black, involves or is related to an ideal black body. Basically, energy that goes into our material in the form of light is completely absorbed and transformed into heat, thermal energy. Based on the law of conservation of energy, mathematically it can be described as a radiation transfer equation of
wavelengths. For example, absorption is the light coming into the material or that is absorbed by the material, and then we have scattering within and from the material, and then the emission, which is the transformation to heat.
One of the most common paints used for black body applications is the benta black. However, this type of paint becomes brittle under some temperatures. In our end, one of the objectives that we have is to find a new method of paint that would resist these temperature changes. Another thing that we need to assess is the absorption of the radiation with different tools. We have our thermal imaging, we have our infrared gun, our illuminance meter as well. And we need to investigate the absorption effects on different materials. We used aluminum, we used PLA, we also used the egg carton, and we processed differently each one with different surface roughness as well as geometry to see how the radiation would be absorbed and reflected as well.
And for our material design process, when we started coming up with ideas for this, one thing we noticed is that different plastics and different things all have a different surface roughness, and that surface roughness basically had a major impact on how it absorbs light, mainly because light scattering across the surface can help to redistribute light across the entirement of the body so that it's easily absorbed by the black material.
We picked aluminum as our casting object because it has high roughness that helps with the paint adhesion and light scattering. It's also low cost compared to other metals. High thermal conductivity to distribute heat produced from the lighting system. It's lightweight, easy of machinability, and it's experienced metal that we use here at UTEP. Now, white casting. We use casting because it has high roughness average compared to other materials processes. And materials roughness is important because they are surface defects in where paint can adhere better to the metal and increase light scattering, making the object even more darker. Now we're going to show you a clip of the metal casting process.
It's not playing on the.
It's not sharing. In our end, it's playing, but not in the presentation.
So basically, you want to describe what's going on?
Alrighty. The guy on the bottom is wearing a heat resistant suit. He's pulling a crucible full of molten aluminum. And the two guys in front of him are going to transport that molten aluminum to the sand cast.
So what we performed were dry runs, and each material that we have tested on, a thermoplastic formed egg carton, sand casted pure aluminum, and 3D printed PLA. We used thermal imaging and also used our light source to absorb the reflection. And we did a sample size of 5 runs per material. Basically, we wanted to emphasize that our project is based on the law of conservation of energy. We have an equal amount of absorption as well as theoretically, that absorption of energy would be produced or transformed into thermal energy. For example, our first material is black aluminum, which was spray painted with Burr spray paint. And when referencing to white PLA, what we did is we did infrared readings of different locations of our sample. For example, the center of the sand cast, the concave where it's a hexagon, but it's actually curved. And then the edge is the top part of our sand cast. On the right shows our thermal image where the heat is basically distributed in our sand cast.
And we did these tests for all our different samples. And so this one shows our 3D printed PLA plastic painted black. And so one thing you can notice is that the different temperatures across the center, the concave and the edge, and notice how the concave has the highest temperature reading. We believe that is due to the transfer of energy between heat and light. And this one shows the plastic thermoformed concave shape. And if you notice, compared to the last one, it's like a huge bright spot in the center. And that shows how there's an evenly distributed temperature across both the center of the concave and the point of the plastic. Similarly, the same results happened for the egg carton. We were getting higher temperatures for the egg carton and the plastic, but we believe that's due to just the material nature itself, not necessarily because of the light absorption. And our final design, which had a few different state faces on it, but both featured a hexagonal with a flat center, a rhombus shape, and then another hexagonal with a cone center. And the one that performed the best was the cone center. You can see how it's a little darker, and it has a pretty decent heat transfer.
So as we previously said, our hypothesis was that concave to hexagonal design can demonstrate properties of an ideal black body. As we went through the testing, we actually did see how the different designs can affect, as well as different surface roughnesses can affect. So how it was previously stated, the rhombus and the conical design did perform the best when it came to light reflection in the honeycomb. From there, we just tested different aspects of it, adding the dimples, and then just different orientations for the product. So we do wish to advance in our design. One way we were thinking of doing is a stamped aluminum sheet. In a way, it's a little more cost-effective production-wise, and it's able to be put up a little more easily. We will be improving on efficiency costs, and also hopefully to yield better results with these better future outcomes. And we would like to acknowledge everyone listed here. Of course, there are a lot more people other than this list that have helped us in many ways that we cannot begin to be thankful for. So if any of you are watching, we really appreciate everything you have done.
Thank you, Tony. Thank you, Randy Anaya from Gaia. And thank you, TSGC. And thank you for our professor, Dr. Smith.
All right, thank you very much, team. So we already have some questions here. So Tony wrote, excellent work, team. Which solution looks like it may be the best optical and cost-effective treatment for darkroom applications?
I'll go. So basically, I think the one that would look best was the 3D printed PLA plastic with the design that had a cone in the center. That one looked the best because it was a cheaper plastic, and also because it could be tiled to cover up an entire wall and possibly scaled to match whatever size needed.
We also observed that the sand cast aluminum also had a more uniform distribution of heat, thermal heat, that basically that was absorbed from our source of light.
So why do you think the one with the cone in the middle was the best? I mean, what design properties make it better?
So based on visual appearance, it looked like to have the most darkness during our dry runs, and also it did have a more of a thermal exchange within the center of it compared to the other PLA plastic designs. And so one thing we also think, the reason why we think this is because the light scattering help with the cone surface, so it's not more of a direct interface facing coming from the light source, but it's more of like an angled slope.
Basically, the surface of the cone, it is not perpendicular or normal to the light source. So basically the light would be more scattered or skewed. So we thought geometry would help with that.
All right, great. Looks like it did help. Could you talk about, based on this other question, the purposes around creating the black body? What uses could it be used for other than the dark room?
One of the uses for the black body in space, the radiation coming from the cosmic rays and the solar rays is affecting, it's the tools that are used over there, anything that has to deal with electronics, they're impacted by that radiation. That's why we want to find a perfect black body or an ideal black body, so all that radiation is absorbed and not going through and hitting the electronic devices. Another thing that we were thinking of doing in the future, this upcoming semester, is actually taking advantage of that energy that's being absorbed instead of just staying in the material, to actually use it either for more devices, change it to electric energy. Or that's what we're thinking at the moment.
I would like to add to Kevin. So basically we learned that the lunar South Pole, it has very harsh conditions. So we learned that at Johnson Space Center, they have a laboratory, a dark room where they facilitate their testing. So basically we're trying to mimic, or NASA trying to mimic this testing environment on Earth to replicate on the lunar South Pole. And we need an ideal black body to absorb, or close to absorb, that thermal energy so that humans can withstand or be comfortable in that cold environment, basically in a architecture building where heat can be insulated, in other words.
All right, great. Thank you very much, team.
You're welcome.
Thank you.
Thank you. Thank you.
All right, thank you, everybody out there, all our audience, our faculty advisors who worked with the teams all semester, the NASA mentors, all your collaborators that work with the teams, our judges. If you would, go to our website and help provide feedback for the teams for their videos, their posters, and their presentations. The audience on the webinar, as well as YouTube Live, thank you for joining us. And of course, the students, thank you for putting in a lot of work this semester. We will look forward to seeing these teams, what they come up with next semester to continue. And thank you again, everybody, for watching day one. This concludes day one. Please join us tomorrow at 1 o'clock for another 9 teams for the Texas Space Grant Consortium Design Challenge. You can learn more about the challenge at our website, tsgc.utexas.edu/challenge. And if you want to learn more about Space Grant in general and all the other states that have space grants, go to our foundation website, which is spacegrant.org. Good night, have a good evening, and see you tomorrow.